Hello, good morning. I'm Reimer and I'm the chair for the next three talks. Please welcome Federico Marani, right?
Yeah,
He gives a talk about feeding data to Redshift with Airflow.
Thank you. My name is Federico. I'm actually from a town not far from here. So it's a town near Modena, and it's very nice to have EuroPython so close to my hometown this year. I'm here to talk about a project I did with a startup in London, and it's one of the first projects I did that was very data focused. So essentially, I'm here to talk about some of the experience I had with data in the last 7-8 months, and some of the tools I used and some of the choices that we made, both in terms of architecting the system and in terms of using the tools. So the talk is about Redshift, which is a database, and Airflow, which is like a framework to which I'm going to explain later. So my background is actually kind of web development, and I also done a lot of DevOps in the past. I've used mostly Django. I've done another presentation at EuroPython 3 years ago, and it was all about Ansible, which is a tool I really enjoy, and I encourage you to have a look at it because it's quite nice. But then data pipelines arrived, and then I had to we had to choose a different stack. It was a project where a lot of data processing was happening. There was no web component, and essentially we decided to choose a different stack. We use Airflow, which is a project that was kind of born within Airbnb, but then it got incubated by Apache, and now it's like an Apache project. And then we use some proprietary tools like Amazon Redshift, which is the big one, and also S3, which is essentially an infinite hard drive. It's like an object storage, and it's very well known. So we started from obviously we started from a product problem, and the product problem was about tracking actually the attendance of conferences around the world, and we were focusing on technology. So we wanted to understand who was going to what conferences in order to present this data and attract sponsors for conferences. So it was quite an interesting project. But then really the technical question that we wanted to answer was, how do we query and cross-reference multiple external data sources? Because most of the data that we were working with was not managed by us. It was external. So we kind of needed to bring the data in our control. There was a lot of integration, so there was multiple external data points, and we just wanted the freedom to query and cross-reference all these data sets. And really the answer to this question is actually, in principle, it's quite simple. You just have to download all the data feeds, so you have access to the kind of raw data. So you can do any sort of operation when you have the raw data. Plus, you need to load them in a system which allows you to query the data in the way you want. This system can be anything, can be Excel, can be PostgreSQL, but we decided to use Redshift because kind of our use case, the type of queries that we wanted to run were like a good use case for Redshift. So yeah, I mean, essentially those are the two things that you have to do, but depending on the complexity of the project, sometimes there are multiple downloaders, there are multiple databases, So essentially, like, you need to make sure you build a good system to manage data, and here we talk about data pipelines, which is a generic term, and it just indicates like the system that kind of supervises all the downloading and all the loading in the database, and all the kind of transformation that you do on the data. And we work on these pipelines, like, kind of following like some principles, like three principles. First of all, we needed a system that was able to scale to any number of inputs. We needed a system that was generic enough to be easily adaptable to any sort of feed, any sort of data coming in with any sort of mechanism. And you can think of it as a mixer. So like essentially you have a lot of inputs, and then you just mix and match kind of the way you want it. This is opposite to, for example, like a web app where there's like a plurality of outputs, like a different output for different users. But here, like, it's kind of reversed. So you have many inputs, and you have like one output, which is kind of the database, the structure that you want in the database. So it's very important, like, for data pipelines to do all the processing in stages, because you might actually have like quite a complex set of transformations. So if you think in terms of stages, it becomes very easy to kind of state what sort of input you have and what sort of output you expect the stage to produce. And you just build your pipeline in a way that each stage does a particular thing, a particular type of process. And then if you do it that way, you get hopefully reusability of stages. You can separate development stages, like between different teams and so on. And another other principle that we used is that we should archive everything, especially the inputs of the system, because storage is cheap. Like, you can store a lot of data on S3 and you don't pay that much. So it was very helpful for us to have like an historical record of everything that was going in the system. And the other purpose of it is that sometimes you have bugs in your code, and for data pipelines you want the ability to kind of rerun your code on data that was like a month old or 2 months old, because you realize you have the bug that we're talking about has been in production for like 2 months, and then you discover the bug, and you want the ability to go back and fix the output. And this is something that you can only do like with data pipelines. You can't really fix an HTTP 500 like in your kind of web application, but you can do this with data. So it's quite convenient that you have that possibility. Okay, so the tool we use is a tool called Airflow. It's a project that has been incubated recently in the Apache Software Foundation. It's a batch processing framework, opposed to like a streaming framework, like Storm. I know yesterday there was a talk about Storm, but here we talk about batches. And essentially, the big difference is that, with a streaming architecture, every transformation is scheduled at the start, and then data goes like real time through the stages. But with a batch processing framework, it's different, because each step is only scheduled when it's actually needed. So yeah, it's kind of a different architecture. Like in my eyes, it's a bit simpler, and it's also like probably the oldest type of architecture, and more sound. Airflow has a big community. There's a lot of stars on GitHub and lots of companies using it. But yeah, I mean, really, Airflow allows you to kind of build this sort of network of interconnected tasks that you run. And you can build like very complex network. You can have things run in parallel, things run sequentially. I mean, this example here, which is like an example I found on the internet. Essentially, you get approval files, and then you start 3 parallel scrapers that are scraping different things. But then at the end of every scraper, there's an update which is specific to the scraper. And with Airflow, you can build these sort of networks of any complexity, like some quite complex, some a bit simpler. And it's Python all the way down. So like it's written in Python, and you use it with Python. But then you would say, like, why not using cron? I mean, cron has been around for ages. The problem with cron is that it's very simple. And for our use case, it was too simple. Like, there's no way to define dependencies between jobs, as in, like, only start job B if job A has been successful. You can't do that. There's no retry mechanism, and there's very, very simple error reporting. So it was too simple for us. So obviously we decided to use Airflow. So the way you install it is very simple. You just pip install Airflow as it's written in Python. You initialize a database, which is, so Airflow is a very stateful application. Essentially it tracks execution of everything that you've kind of put in the system, and all this information is written in the database. So yeah, it just needs a database. And then you start a web server, and then you have something like that. So this is a UI of a system kind of we have in production. And essentially, it just lists all the workflows that you have. Workflows is a term that is roughly like a cron job. So every workflow has a name, as an owner, and as like the schedule, if it's daily, if it's hourly, if it's, you can define, you can be very flexible in defining when something needs to run. Yeah, I mean, it's actually quite simple, and the UI is quite powerful. There's a lot of things you can do with the UI. But I wanted to show you, like, how do you actually use Airflow. So Airflow, as I mentioned before, is written in Python, and you essentially create these files called DAGs. DAG is an Airflow term, which essentially is workflow, means workflow. You create, you create a file with Python code in it, which essentially instantiates a DAG class, which declares kind of the workflow name, and then you pass a few parameters. One of the most important one is the schedule interval, whether you want it daily, when you want it hourly, and so on. And then you start to compose your workflow by creating tasks, which are instances of operators. The operator is the thing that kind of tells Airflow how to run this step. And yeah, I can more on that in the next slide. So essentially we run two bash commands in this case. One is to generate a report, because the workflow is about kind of generating reports for the business team. It's just like an example use case. So the first step would be to generate a report, and the last step would be to email the report kind of to the business team. The second task needs to always happen at the end of the first task, and only if the first task succeeded. So essentially, that's the way you do it. You just declare a DAG, you declare the 2 steps, and then at the end, you just say, like, T2 set upstream T1, which means that T2 is always executed after T1. Yeah, essentially you have this very simple DAG. You put the DAG in the DAGs folder of Airflow, and then it just gets picked up automatically, and I mean, for this tag, it will be executed hourly. And then at the end of every hour, you have an execution. For like this different types of operators, you can launch bash commands, you can launch kind of Python functions. That's an example there. And this is like the two most common things like that can be used in the project. But I know you can use like this Docker operator that you can use to launch Docker containers. And there's also something called sensors, which essentially is a specific like a special type of operator that is waiting for an event to happen, which might be like a file uploaded to S3 or any other sort of thing that you need to wait for. Everything is templated in Jinja, so you can have, for example, like kind of Python files with, essentially variables there that can be substituted on the fly by Airflow, or the same for bash scripts. I mean, this is like quite helpful, for example, if you want to pass variables from Airflow itself to your scripts. Or alternatively, you can use like, you can pass as arguments to Python functions, like the example, yeah. So I want to kind of delve a bit deeper into like how actually Airflow works internally. So everything, as I said before, is visible through the UI. So you have essentially, you can see every execution of things in the past and the result of it. So for example, if you have a workflow that runs daily, you will have in the UI the possibility to see all the statuses, all the results of every execution of the script, going back from today to the date that the script started running. And yeah, you can zoom in and you can see, for example, for every task, there is a task instance which is like a database construct, which essentially stores the start time, stores the end time, the duration, and the state, whether it's been successful or not. Yeah, it's very informative, especially if like kind of one of the main things the company does is data processing. So how does Airflow like runs all your tasks? So you can choose like mainly two types of scheduling. One is kind of scale up using like a pre-fork model, like what Apache or Nginx, what all the Unix daemon do. Essentially, they just have a parent process which forks like 4 or 5 child processes, and then the parent process like pulls for new jobs, and when you have a new job, a new task, the child process will execute the task and track the result and write the result back in the kind of Airflow database. This works very well for like one server. If you have the need to scale to multiple servers, you can use a kind of serial executor. But like it's definitely more complex. You need to have a message queue. You need to have a bit more installed. But you can definitely use it. So regarding all this information that the system is tracking, yeah, like essentially, like you have like a lot of information, and one which is the state. So you want to know when things are running, you want to know when things have finished running, and you want to know whether they were successfully run or they failed. And if they failed, Airflow has this kind of mechanism of like retry. You can definitely specify like how many times you want the DAG to be retried, and you can also be more granular than that, and you can specify like how many times do you want a specific task to be retried. And if there is a retry mechanism, there's a couple of states. One is retry and one is failed. And retry is like, it essentially means it failed one time, but like I'm going to retry in 5 minutes, like a delay that you can set. And those are kind of the state machines, the states. So another concept I want to introduce is that, and it's something that kind of differentiates Airflow and cron, for example, is how Airflow deals with time and specifically downtime. So the default behavior is to backfill when where runs were supposed to run but did not, which essentially means if you have a cron job or like a workflow that is meant to be run daily, but then your server stays offline for a week, when the server comes back online, essentially Airflow realizes that for the last 7 days the job wasn't running. So we launched like 7 copies of your script. And the difference between all these executions is that essentially there's a variable passed to the workflow called execution date. And this variable will contain the date of like 7 days ago, 6, 5, 4, 3, 2, 1 days ago. And this variable is meant to be used from your scripts to limit the amount of data that you process. I mean, this is like a very good behavior for example, like kind of report generation, like for the business team, because the business team doesn't care whether the server is up or not. It just wants to receive a report every day. But it's actually quite bad for scrapers. We are running like a lot of scrapers, and we don't want to run like 7 scrapers at the same time. We just like, first of all, it just kills our server, it kills their server, and we don't get we get exactly the same data. So we started using an operator which actually was released in the latest version of Airflow, I think. It's called latest run only operator, and essentially it skips all the past runs. It only runs the latest copy. Okay, so that was about Airflow. But like, essentially the way we use Airflow is to do like extract, load, transform, and more specifically, because of the tools we picked, we have like a bit more of a general structure, like a specific generic structure. So we started generating batch IDs because we want to track every run of our code, and we want to see what a specific execution, what sort of data a specific execution is generating and putting in Redshift. So we generate a batch ID, we create an initial folder structure, we run like kind of downloaders and a structure like whatever we want to run. This is normally the step that takes the longest. And then whatever comes out of that, we compress it, we upload it on S3, and we load it in Redshift. That's essentially like the generic steps that we used to follow. So I mentioned batch IDs, and for us was like, I mean, generally it's quite important to generate a batch ID because you want to track, essentially, you want to be able to map back the data that you generated to the specific run for debugging purposes, or like if you want to fix a bug and go back and fix the data that this bug broke, like you need to know what batch IDs were involved, and so you can remove the batch IDs and you can regenerate the data. Another reason to have batch IDs is that Airflow may rerun some of the steps, including loading Redshift. So it's very important to have to make this operation idempotent. So it doesn't matter how many times you do it. The result will be always like one and only one load in the table. So we timestamp all the data. Again, very useful for like debugging. You want to know what time it was downloaded, you want to know what time it was written in S3. Yeah, and so on. So we did all this operation. We got to, kind of run our downloaders. We got to we got some data on the hard drive. We compressed it. We sent it to S3. But then, because we want to use Redshift, it's quite important that we pick the formats that Redshift supports. So there's two family of formats in Redshift. One is like column-based, and the other one is row-based. I'm not going to talk much about column-based. First of all, it's a bit less common in the Python world. I know there's Parquet and there's ORC, I think. But the support in Python is not great. It's not as supported as row-based formats. And also, the row-based formats are generally more common. So row-based formats are essentially three. One is CSV. The other one is JSON lines, which is like a bunch of JSON objects separated by new lines. And the last one, and also the most recent one, is a format called Avro, which is like an Apache standardized format. So CSV is very simple. Everyone knows what it is. Unfortunately, it's order dependent, it's flat, and it's quite hard to extend unless all you do is append data to the end of it, which is quite limiting. And it's also untyped. So yeah, it was a bit simple for us. JSON lines, again, it's very simple. Everyone knows what JSON is. It's easy to extend because you can just add keys to the JSON object, and it should actually still work. It's a bit verbose unless if you don't use compression, but you can use compression, so we can remove that. It's schemaless. It doesn't enforce a key being there or a specific type, which might or might not be a problem for you. So the last format is Avro. It's not so common. It's quite easy to extend. I think with Avro there's schemas, so you can enforce keys being there. You can enforce some types. Unfortunately, it's a bit smaller ecosystem. And in our project, we decided to use JSON lines. So it's very simple, and it was good enough for us. So we got to the point that we kind of save all this data in Redshift, and then let's talk a bit about Redshift. So Redshift is a product created by Amazon. It's not open source. And essentially what they did is they forked PostgreSQL, and they made it work for OLAP workloads, like analytical queries. But they changed quite a lot. They changed the query plan, and they changed the storage engine. And essentially, it's like buying a car and changing the engine. It was quite a big change. And they made it work well for huge volumes of data. It has very good on-the-fly compression support. But then it's like a columnar database. So which means for the kind of things that you would expect like a row-based database to be fast, actually Redshift is quite slow, given the right volumes of data. And the opposite is also true for the things that they're slow on Postgres, they're quite fast on Redshift. For example, aggregate on single columns, having many values in that column is actually quite fast for Redshift, but quite slow on PostgreSQL, for example. If you do lots of insert updates on single rows, it's definitely slower than PostgreSQL. If you select a single row and that row you want all the columns, that's quite slow in Redshift. And it's because like the biggest difference is really like the storage model. The Redshift is a column disk, uses a column disk layout, and Postgres has like a row disk layout, which really means like when you have a table, like the way Postgres writes in a disk is like traversing each column row by row, like in kind of a horizontal way. And yeah, that's the result you get. But like with Redshift, the traversal is actually reversed. So it traverses all the values of a column. And then when it reaches the end, it does the second column, the third column, and so on. I mean, this is pretty fundamental, and that's why performance is reversed. Yeah, and that's why queries that are slow in PostgreSQL are fast in Redshift. The other big difference is that the block size is normally quite big, so you can load a lot more data in memory at once. While with PostgreSQL, you have a different like many different cycles for like many different loading steps. And I mean, considering that the database, like the most critical part of a database is loading data from an hard disk to the memory. I mean, this is quite big. Okay, so that was Redshift, and but like, how do we actually use it from our system? And so Redshift has very good support for S3, and if you have the files on S3 of a format that Redshift supports, it's just a matter of like executing an SQL query. Is a copy command. You specify the destination table. You specify where data should be read from, and you specify whether it's a JSON file or not. I mean, in our case, it's a JSON lines file, and gzip if it's compressed. And what this query does is like 4 things. One is reading data from S3. Once it's read, like it decompresses data on the fly, and then it does something called like JSON path flattening, which I'm going to explain in a second. And then whatever comes out of this third operation is then appended to an existing table. So it's loading this data in the table. So JSON path flattening is essentially an operation that takes a nested structure like JSON. You know, with JSON you have like key values, but then a value can be another object. So you have like another set of key values, or can be an array. And essentially, like, you have a lot more nesting. But then if you think about Redshift is still like a relational database. You have tables, and tables are like a flat structure. So like the way the way we decided to do it is using JSON and JSON path, which essentially, when you apply this file to a JSON lines object, it will generate like a sort of CSV with 5 fields. The first one being the value of the key ID. The second one being the first element of the array of the value of data 1. Then you have like subfield of data 2, and so on. So at the end of this, you have a flat structure that you can just append to a table, and that's the way we did it. Another thing worth mentioning is that, like, you know, for any software project, the schema of the database is quite important. We wanted to have the schema kind of versioned and storing it like you probably would with any other infrastructure code. If you're using Ansible, you want Ansible to be in your repository. If you use Terraform, the same thing. And the schema is just another one of those assets that you really should put in Git and version. So yeah, we definitely use SQL Alchemy. we don't rely on SQL Alchemy too much to do ORM operations because it's not the use case of Redshift. I mean, you can still create queries using SQL Alchemy, but like we don't really use models in that way. And the other benefit of having SQL Alchemy is that you can, it just nicely integrates with a migration framework called Alembic, which is quite complex and quite kind of featureful. But essentially, like with a migration framework, it's really two operations that you tend to use. One is Alembic revision, which generates migration files. And once you have these migration files, you can run this migration file on the current schema to upgrade the schema or downgrade the schema, depending what kind of direction you want to go. And to apply these files is just a matter of running like an Alembic upgrade. As I said, it's quite a complex framework. It supports multiple environments. Auto-generation only works sometime because Redshift is definitely, as a lot of edge cases, is a bit weird sometimes. Especially, for example, when you alter columns, like you cannot really alter columns in Redshift. You have to drop columns and re-add them, which has a lot of consequences, which gets me into these annoyances. Redshift has a lot of things which are quite annoying. For example, like the virtual length is expressed in bytes instead of characters, while for Postgres is expressed in characters. So sometimes you have edge cases where like you kind of scrape sites with Japanese characters, and then suddenly like the loading breaks because kind of the Japanese characters are mostly using the Unicode extension, so you probably have 2 bytes instead of 1 byte, and that was really annoying for us. You can add column types, as I said before. Referential integrity is not really a thing in Redshift, so primary keys and foreign keys are not really enforced. But that's okay because we don't, for our use case, we don't need it. And columns are nullable by default, which I think is different in Postgres. Is this system future-proof? Yeah, I mean, we're reasonably happy with it. Redshift Spectrum came out, which seems very interesting because it would essentially mean that we could potentially skip all the loading in Redshift because Spectrum reads data directly from S3. There's like a couple of open source projects which we might look at. One is called PressToDB, which again is able to run queries directly on S3 without you having to kind of ingest these files in a database, which is quite nice. And we don't stream to S3, which might be like a good thing to look at. And there's another project which I want to mention. It's actually an extension to PostgreSQL called Cetus. And it's done kind of by a company in US. And like if you are a fan of PostgreSQL and you want to kind of use raw, like the original PostgreSQL with all the extensions that you kind of learn to like, you can look at this company, Cetus Data is called. Thanks a lot. I think that was it. I actually want to mention, like, I'm actually looking for work, especially on kind of this sort of stuff, because I really enjoyed it. So if you have, if you have like a project like that, you want to kind of talk about it, I'm happy to talk about it. And I mean, that's it. Thank you very much for listening.
Okay. Now, so any question to Federico? And yeah, thanks for your talk.
All right, thank you.
So if you speak to the microphone, it goes in this direction.
Oh, okay.
So you can walk to him and talk to him.
Oh, yeah.
Yes, but with the microphone, yes, please.
What do you mean?
No. Federico?
Hi, can you hear? No.
Understand anything in this place. So there are questions to you. So, and he was speaking. So, but I think you didn't hear him, right? No, sorry. Yeah, it's okay. 1 minute? Okay. Okay, welcome. We have the next talk. It's about visualization data that includes geographic locations. It's by Guillem. Oder he can say his name much better than me. So, and it's yours day.
Okay. Is everyone ready? Hello, everybody. It's a pleasure to be here. Today, I'm going to talk about maps. But first, let's start talking a bit about myself. My name is quite weird to pronounce, so I will just present myself. I am Guillem Duran Ballester. Oh. These are my Twitter and GitHub accounts. And when I was younger, I wanted to be a hacker. So that's why I studied telecommunications engineering. But for the last 5 years, I've been more focused on learning Python and data science and trying to invent my own artificial intelligence algorithms. I'm currently working in Madrid at Source, which is a really cool startup, but I am from Mallorca, and I'm actually really proud to be one of the organizers of the meetups on PyData that we hold there. Why I'm here? Well, now it works actually better. You hear me well? Yeah. A few months ago, Bial Estela, who's a friend of mine, found InsideAirbnb.com, which is a website that periodically scrubs Airbnb and makes the data available to the public. He wanted to study how Airbnb influences the real estate market, but he had no way to make cool visualization about his findings. You can see here how InsideAirbnb collects datasets from all over the world, but mainly from North America and Europe. And well, we also have some datasets from Australia and Hong Kong. Each one of these datasets contains 92 different columns with a very wide range of features, such as how the information was scrapped, listing features about the daily price of a renting, how many bedrooms or bathrooms it has, and so forth, and also has location features, like the GPS coordinates that I displayed on the maps in the Inside Airbnb webpage, the booking requirements that an owner makes to be able to rent his listing, and also information about how the people who rented a listing reviewed that listing. We will be using data from both Mallorca and Barcelona, and well, each one of these datasets contains 14K columns and 17K columns respectively, so it's in the range of what a browser can handle easily. So this could not be considered big data. This is one of the visualizations that the Inside Airbnb webpage has, which shows how the Airbnb listings are distributed in Barcelona. Here, for example, you can see in green listings that correspond to a whole apartment or house. In red, you can see the ones corresponding to one room, and there's a few one here in blue that corresponds to rooms that I shared. If you go to the website, you can see the same representation, but for data from Mallorca, and you can inspect it, zoom in, and it actually works quite well when you have enough RAM, and has cool tooltips and filtering options. But I think this is written in JavaScript, and this is EuroPython, so I wanted to make a tutorial on how to display this data. Plotting maps is easy, but it can really be a pain in the ass if you don't know how to do it. So I wanted to make a tutorial for people that wanted to try to plot geographical locations but had no idea how to start, so I can at least save them a few hours if they just download the repository and clone it. So today, we will talk about how to plot Google Maps using bokeh, how to work with shapefiles, which are a data format to work with geographical locations, how we can plot these shapefiles using HoloViews and GeoViews, and how we can use big data to make cool representation with data shader. So let's get hands-on on the notebooks. These notebooks are meant to be used with any data set available in inside Airbnb, but as I am from Mallorca, I will be mainly using the data set from the island. So how many of you know bokeh? Please raise your hand. Okay, there's a lot of people here. Well, the ones that you know, please check the documentation. It's an awesome package for making any kind of visualizations. And the ones who already know it will find it extremely easy to work with Google Maps. It is basically like building a regular figure object, but with additional features in order to indicate how we want our maps to be displayed. We will need to input the latitude and longitude coordinates of the center of the map, the zoom level, ranging from 1, which is for the whole world, to like 20, which is the max zoom you can get on a Google Maps. You also will need a JavaScript Google Maps API key, and you also need to state which kind of layout do you want your map to be displayed. For example, we have the roadmap layout, which is like the map that we all know. We also have the satellite layout, which is more like a Google Earth style, and the hybrid layout. Then that is just like the satellite layout, but it also has an additional layer. Well, let's wait for the internet to load. Let's get cable. Now, this is the last layout, the terrain layout, which is almost like the roadmap layout, but with an additional feature that highlight terrain features. And the one that I wanted to show you before, which is the hybrid layout, is just like the satellite one, but with an additional layer which shows roads and names of places. So once we have created our plot, we will go for the first example. In this example, I will try to recreate the plot. To recreate the plot from inside Airbnb. So now that we have the roadmap layout, we need to embed data on top of it. This embedding will be done by creating just a regular scatter plot. Well, we will assign visual properties to each one of the points. So first, we will select a suitable color map in order to mimic the plot that we are going to replicate. So we will select a diverging green, white, red color map and assign it 3 colors. And now we only need to create a scatter plot where the x and y coordinates of our plot will be the latitude and longitude coordinates from each one of the listings. And we get a pretty cool plot, which, given the amount of code that took to build, looks actually pretty similar to the one that we had here. Of course, this can be improved, having filtering and additional and more worked tooltips, but I think it's actually pretty good. Well, we're working with a number of points that can be managed by a browser easily, but sometimes it comes in handy to aggregate data over regions. As we cannot trust the region data that it's embedded in the data set, we will have to download a shapefile with all the geographic data of all the regions in Spain. A shapefile is a vector format for geographical data representations. Each one of the shape files can contain different records, and each record contains both a geometry and different attributes. This geometry thing is handled with Shapely, which is a Python library that allows to work with planar geometrical objects, and each one of the attributes is stored in the form of a Python dictionary. As we are getting all the regions in Spain, we would like to filter out that ones that do not correspond to Mallorca. So, looking at the record attributes that we have, we find this CODNUT3 code, which turns out to be a standard way for representing geographical regions in Europe. Here you can see all the CODNUT codes that belong to Europe at the level 3, and it turns out that Mallorca is assigned the code ES532. So we whoops. So we only need to iterate through each one of our records and store the ones that belong to Mallorca. Now we have, on the one hand, all the shape files, all the shape records corresponding to the island, and a lot of GPS coordinates. So if we want to match one with the others, we will have to think some way to do it. What we will do? Okay, we will take the Shapely library and create a point object using the GPS coordinates of each one of the listings. Once we have created this point, we will be able to calculate distance between that point and each one of the regions that we already have stored. When we find one which distance is 0, we will just store the name of the region that we found inside the column of the data frame. This way, we will be able to aggregate the data by the regions that we just calculated. And now that we already have the shape files of the regions that we're interested in plotting and the aggregated data, we will use alloviews and geoviews to plot it. Please raise your hand, the ones who know what is alloviews. No one? Oh, great. And geoviews, have you ever used it? Okay. They are actually two really cool libraries which allows to do really complex visualizations really easily, and they can use as a backend Matplotlib, Bokeh, or Plotly. And well, GeoViews is an extension of alloviews that allows for also working with geographical data. So we will load alloviews and GeoViews, and we will create a data set from the aggregated data frame that we had. Now, we only have to select the shapefiles that we want to plot, the dataset, and a series of attributes that will create the visualization. In this case, we will choose on, which is the common key on we will join the data, a key from the attributes of the shapefiles and from a column in our data frame. Value, which is the column in the data frame that will be used to assign colors to each one of the regions. Index, that are a list containing the name of the columns that will be used in the tooltip. Group, which is used to state the name of the plot. And finally, CRS, which is the kind of projection that we will be using. In this case, is plate Curie. Once we have done that, we can use cell magics to state how we want the visual options of the plot to be displayed. For example, we can choose to eliminate the axis, use a hover tool, the size of the plot, or even how we want the colors to be mapped. And here, we can see how we started with a scatter plot of a lot of points, and we were able to map them into this shape plot, where each one of the regions is colored according to the number of listings that it has. For example, we can do more things with that, like aggregating the data and coloring by different properties. So here we have a comparison. Perfect. A comparison of the number of listings in each one of the regions in Mallorca against the median price per day that each region has. For example, here, which is Palma de Mallorca, the capital, has the most number of listings, but it also turns out to be the most cheaper one. So when you have a lot of money and want to be alone, just go to the northern part of the island to Daya. And now, before moving on to data shader and big data, I wanted to show you one cool thing that my friend Biel Estela did. He used the Barcelona dataset and various data sources to try to figure out how many listings in Airbnb there was compared to the total number of houses in Barcelona. Airbnb usually states that it cannot influence the real estate market because the proportion of listings that it has to the total portion of the real estate market is really low. That is true unless you group the data by different neighborhoods. So he first created a plot of all the different neighborhoods in Barcelona, and then merging different data sources, he calculated the proportion of Airbnb listings to the total market of real estate market. And we find that, okay, it's true that if we take the whole city, the proportion of Airbnb listings is really low, but if we go to the center of the city, we found that, for example, in El Barri Gòtic, there's 14% of all the houses available that can be rented using Airbnb. And the colliding neighborhoods, you find that this proportion is about 10 or 11%. So it really has a great impact if almost 1 in 10 houses in your neighborhood are occupied by tourists and available in Airbnb. Well, now that we've finished with HoloViews and GeoViews, let's talk a bit about data shader. How many of you know data shader? Have you ever heard this word before? Whoa, I have one. Nice. Well, data shader is actually a really good package which is meant to make easy plotting big data. There's a lot of examples in the form of Jupyter notebooks that you can just check here. But I will explain its inner workings. It mainly consists on a 3-step pipeline which allows to turn big data into images. How is this process accomplished? Well, first we have a projection step in which we will define an image container. This image will be treated sort of a 2-dimensional histogram and assigned different bins. In the next step, the data will be aggregated in a meaningful way, such as the count, or you can use any aggregation function you want in order to map the data into that bins that we created in the first step. And finally, we can choose how we want the visual properties of each one of the bins to be displayed. Using these 3 steps, we finally get an image which has all the data that we wanted aggregated. For example, if we wanted to show a data shader representation of the listings in Mallorca, we first define a canvas as a projection. Then we use CVS.point with the listings, X and Y axes, and the function that we will use to aggregate the data. And finally, we pass that aggregated data and select the kind of color map that we will use. In this case, it's hot. And we will indicate that we want to map the colors logarithmically to each one of the bins. And then I also choose to have a light gray background, so it's easier to see. And this is what we get. In order to understand better how this binning process works, let's compare a regular scatter plot with a representation of with a data shader image. One moment, Okay, So as you can see here, where in the scatter plot, a high density of points is just represented by a blue mass, data shader allows to change the color according to the density of points. And if we zoom in, we can see how the data is mapped into bins. These are each one of the bins created with an heuristic, and each one is colored according to the number of points that fell into that bin. Of course, this is a pretty aesthetically unpleasant effect. So if you change this dynamic attribute here to true, all the plotting pipeline from data shader will be recalculated each time. So when you zoom in, these bins will automatically adjust to the data that it's included in the image. You have to take into account that the coloring is also taking into account only the number of points that are included in the image and not the whole data set. So if you're mapping data and zooming in, you can see how the map shim changes according to the points that are displayed. So now that we already know how to display big data with data shader, we will explain how it can be overlaid on top of a map. Unfortunately, here we do not have Google Maps, so we cannot access the Google Map plot like we did before, and we'll have to think some other way of doing it. In this case, we need to do a few steps, because we will be using something called tile sources, which is basically a class that if you pass it a proper URL as a parameter, it will just download an image each time that it is called. So in this case, creating the class args from wm_sty tile source and passing this URL, we will later get an image representation. The downside of it is that it uses a different cartographic projection. So if you want to use OpenStreetMap instead of Google Maps, we'll have to transform the coordinates from one projection to the other. In this case, we have created a function that takes data frame as input and transforms the longitudes and latitudes from the plate carré projection to the Google Mercator one. In order to create the plot, a map plot with data shader, it's quite similar to the way that we did it with Google Maps, but you will need to figure out which are the coordinates that correspond to the center of the map. Sorry. Instead of the center of the map, you have to define the ranges of geographical coordinates that you want to have displayed. So it takes a little bit of tweaking, and it's not easy, but once you have found the right numbers, it looks like this. So this map is not as cool as the Google Maps one, but at least you can still zoom in, and all the pipeline is recalculated each time. And the more you zoom in, the cooler you get the map. You have to take into account that even though these are just 17K points, all the time it takes to aggregate the data and use it, it's pretty much similar from this size to like 100 or 200 megabytes. But it's also building an image with big data, like using the Tachi dataset, which is included in the examples that I showed you before, like creating, or the census data, or the census dataset from the United States is actually quite fast. it's a bit painful to install all these examples, but you have a really nice tutorial there on how to do that. It takes a while to download all the datasets, but you should totally check them out because it's totally worth it. But, well, what are the downsides of using data shader to work with big data in the notebook? Well, unfortunately, everything related to interactivity does not work pretty well unless you are using the options that I included in data shader to build widgets, but you have not total control over what you are plotting. For example, I tried to build here a dashboard that showed how aggregating data works with data shader, and if you are just using this image, it works quite well, but for example, if you want to change how you aggregate the data, for example, if you wanted to aggregate the data by the match price of each one of the listings that fall inside each one of the bins, you get errors that you are not able to silence until you get it right and the image is recalculated. And also, please do not use the reset tooltip, because it messes everything up. Well, now it would be really nice. I can talk a bit more about JSON data, and I can show you some examples, but I would really like you to ask questions. So I will just finish my talk here and let you ask wherever you want. I'm not really an expert on this topic, so maybe you think of a question which is quite difficult. I won't be able to answer it, and you can laugh at me. So thank you very much for being here, and it's been a pleasure to be talking about maps. Thank you.
So
If you are, well,
there is plenty of time of question, or you are finished?
I would really like you to ask questions. I can keep talking if you want, because there have been like 27 minutes and I have more material, but please, come on, participate a bit. There's a lot of people in here, so what would you like to know about plotting data on maps?
So hands up, please. Or stand up, that's better. Please speak slow. It's an echo here, and you click on
My question, thank you very much. It was very useful. My question is regarding the shapes. When you painted like the shapes of, I don't know if it was the different regions of Mallorca and the density of points in that area, I had to do that at wall scale. And from the files I've got, the precision was very accurate and the data was massive, and it was impossible to plot anything. So I mean, the shape of the United States, I don't know how many points there are there, but if you have like 1 point every 2 meters, it's like huge, and I never managed to plot anything with that data. Do you have anything to just compress this, or did you have to use anything like that?
I think if you're using shapefiles, you are screwed, because I also tried to do that with the whole regions in Spain, which is not a lot, but it was totally impossible, because I got a lot of lag, and the browser just cannot handle so many points. So you have to resort to data shader, but the good thing is that it can be used to plot data from all over the world. It actually has one example in which it's used data from satellites that shows really well how all this works. But yeah, unfortunately, if you are using shapefiles, you are screwed. So you have to figure out some way. You could aggregate the data and pass it, try to create an image using data shader for the data that you have aggregated, but it won't be easy. So maybe you should contact James Bednar, who's the main maintainer of these packages, and ask him how to do it. They actually answer really fast in GitHub. So if you open an issue, there will be a few hours until they respond.
So, further questions?
It's a Python conference, so you presented Python solution. Is that the best technology to display such solution, such information?
I did not understood you, because when you talk
sorry.
with the mic here, it reverbs a lot. Can you please come down and ask me?
You said it's Python conference, so you presented Python solution. Is that the best technology to display that, or is there some alternative?
It depends on what you want to do. It can, if you're using the notebook, you can achieve almost anything, but if you are a real pro and have a lot of investors worried about how you're displaying the data, maybe you should use JavaScript, because it will be easier to do some really handmade JavaScript tricks that are really specific for the kind of representation that you want. But if you want to build something a bit more general really easily, just fall back to all views and GeoViews, because it's really easy and it takes a few lines of code to do something really complicated. For example, the plots here, a few years ago, I tried to do something similar with plotting all the patches. And it was an example on the first versions of Bokeh about the census in the United States of America. And there were like 70 lines of code, which have to be really carefully thought because it was really easy to mess up. So this is getting every day easier and easier to use. Now, the most pro thing is JavaScript, but if you wait a couple of months or years, you will get the same things here in the notebook. And this can also be used using the Bokeh server. So if you don't like the notebooks, you can try to do it there. It's a pain, but it can work.
Come down.
I almost heard you. Yeah, I would definitely use this to prototype the visualizations, and if you need something really specific, you can resort to JavaScript. But even with things like the tooltips, Bokeh allows to play a lot with it, so you can embed arbitrary HTML code inside of them. So almost anything can be accomplished, but yes, if you are a pro, go to JavaScript.
So, who's the next? Please, can you come downstairs? It's much better to, we need the question on the video too, and also he wants to understand you. So, anyone with questions, please come down.
Oh, nice.
Can you show us an example of how to visualize time series data? Visualize time series data.
Yeah, I do not have it loaded here, but there's an example. Oh, let me think. Okay. Here there are a few examples. For example, here, which is a visualization. Let me zoom in a bit. Whoop. On the population of some cities. You just enter a proper formatted data frame, and as I told you before, there are like custom widgets that can be used with all views and GeoViews, so you can use them to visualize how things are evolving in time on top of a map. Depending on the specific kind of visualization that we're going to use, I can point you some resources, but here you can find a few things about how to do that. And also in the examples from all of you, I think there was well, merging these two examples, you should be able to work with data and maps and make cool dashboards. We can talk later about it if you want. Okay.
Hello, thank you for inspiring talk. I got a question maybe unrelated to geodata, but is there any convenient way to create a custom shaped map, for instance, from TIF texture to get the custom map view, for instance, for some game data, game level data? I mean, is there a way to create a custom map to load and visualize the data over it?
Yeah, what kind of custom map are you referring to?
I mean, for instance, you have a in-game level, and you have a player activity data, and you need to visualize it. So you have an actual geometry with some coordinates. So is there any way to load such a level right into these tools?
Yeah, there are actually very different ways to deal with all these things, but there's a package called Cartopy, which allows you to get images in all of the coordinate representation that you need. Let me check for an example. Well, for example, here there are different types of visualization using Cartopy. For example, you have like the whole world map here to be plotted with Matplotlib. Take into account that all the weird projections and all that, I'm not sure if it works with bokeh. Maybe you have to do it by hand and be converting from one coordinate system to the other in order to then plot them as a scatter plot. But Cartopy has not only everything you need to switch from one coordinate system to the other, but also has stored visual representations of maps. So in a similar way as we did with the Google Matplot, you are able to select how you want your maps to be displayed. Wait a moment, let's see if I can find yeah, here you have a lot of different map representations, so it's really possible that you are able to find the one that you need. And if you're not, write Jens Bender, bother him.
Okay, can you come please down for questions? You have one? No? Any
You want me to
question?
torture you with GeoJSON data? Nah, that's just a joke. I
No.
won't.
Yeah. Oh, that's easy.
Do you know if it's possible to integrate OpenStreetMap with bokeh, for instance?
What is it? It should be possible. I have not tried it because I think that Google Maps are way cooler, at least the point in which they are now. But I can look at it and tell you later. We'll try to search it. I have never done it myself before.
Okay. Next question, 2. Any question? Okay. Can you come and speak to the microphone and directly to him? Otherwise, it's difficult to understand for him. The microphone is for the video.
Yeah, it's like the mic is for the people in YouTube, but if you use that, I cannot hear you well from here, so.
If you put the data into a bokeh, what do you get? Is it some kind of JavaScript, or I didn't understand it really?
I'm not understanding your question.
I saw all those bokeh calls, something like this, and some map mysteriously appeared. What do you get if you put data into bokeh? Is it some kind of JavaScript that you can put on a website, or? Yes.
Well, if you wanted to study thoroughly all this data from Airbnb, first go to the repository of my friend, who's this one, because they did an in-depth study on how data from Airbnb affects the market. And if you wanted to plot it outside the Jupyter notebook, you would have to use the bokeh server. It's, I don't like it because it's really difficult to configure for me at least, but it can work really well if you know what you're doing. So you could also be using data shader, Holoview's, and GeoViews, using bokeh as a backend, and using the bokeh server to render the plots and then send them as HTML code and JavaScript into a regular website. Because bokeh is using JavaScript as a backend. So if you're using the bokeh server to render the plot from bokeh looks like regular HTML code that you can embed in your website.
Last chance for a question.
Yeah, you can find all these notebooks on GitHub. So when you want to plot maps, just clone the repo and copy paste. And if you want to know the findings of my friend when he analyzed the Airbnb data, then go to this repository. Mine will be in my, is this one. My username in GitHub is gmdb, and the project is inside Airbnb EuroPython 17. And here you will be able to find everything that I explained here.
Please come downside. No. Please speak to the microphone, but directly to him.
I wanted someone to ask me this. I did not forget to put the data into the repository. It was too big for a GitHub repo, so I have uploaded that into my Google Drive account. So I don't know which is the link, but I will put it in the repository, okay? I don't know where it is. Now, here. See, I have all the data inside the zip file that I will commit to my repository when I finish the talk in about 10 minutes or so, okay?
So, last chance. Otherwise, get him for a coffee or so.
Well, it's been a pleasure having you as a public, because it's like the time that I have been asking more questions in my entire life. So thank you very much, everyone.
Please welcome Omar for the next talk. It's about non-parametric Bayes.
Hi, I am Omar Gutierrez. I want to talk about some things for non-parametric bias. Most of the things I will say are based on some tutorial from this researcher, Samuel Gersman. Actually, I won't tell you too many things. We will recap somewhat the definition for a model in a nutshell. And I will show the most simple example for non-parametric bias that is clustering. I will show you how we usually do the clustering and the alternative approach, that is the non-parametric model. And, well, I will say something at the end. I will try to say some jokes. I hope you understand. Okay. What we do in machine learning is, how can I say, not only, but the main idea is to modify the values for some parameters in some training process. Well, this is almost the default approach in machine learning. So it's not common to hear parametric models, but almost all models that we are using right now are parametric. But there are another group of machine learning models that are non-parametric. And for me, they are very interesting. I think we need to discuss the idea. So just to remember that in linear regression, our parameters are, well, our beta values. So we can move a line in the plane or a hyperplane. And, well, in neural networks, it's almost the same. But, oh, well, this is a perceptron. I confused the image. But it's the same. We modify the ways, etc. Also, I don't know, hidden Markov models. We have some kind of ways that are the hidden values, and we modify them. So then I think you know so much about machine learning. So I want to ask you something. For you, which one is the best model? Think on the blue line as, I don't know, a kind of time series, and the red line, the model. So for you, how many of you think that the model A is the best one? And how many of you think that the model B is the best one? Okay, well, I did a trap because I didn't show you the complete data. And, well, in the last step, we can see that the line blue dropped down dramatically. So in this case, the best model is the red line. No, sorry, the one in the letter B. So then it's not so easy, like just modify parameters in a training process. Data science sometimes is rather than a science, it's an art. So let's think, I don't know, there is someone from GIS here. Those guys are doing stock marketing. So imagine that uh, we are buying the stocks, but in some moment you need to stop buy it because it could be risky. So the model in the side B is a good model in that kind of scenario. But maybe you are asking why this name, like Bertrand Russell's inductivist Turkey. Do you know the history? Okay, so it's very funny because imagine that one Turkey that is smart, this Turkey it has this philosophy, inductivist, so he makes conclusions, and then each morning he receives food from his owner. Then he started to think, oh, okay, I'm receiving food at night, in the morning, the rainy days, sunny days, weekends. So he started to conclude that he will receive food for a lot of time. But that is not the case in Christmas Day, because the next day the owner will cut the throat for this turkey. So this model is very good in that scenario. And I like that history from Bertrand Russell. So I think that you know this formula, of course, the Bayes rule. Well, I will recap. I will repeat what it does mean. Well, let's start with the blue term. That is our prior knowledge. Imagine that as the conclusions that the Turkey is getting every day. So, but this reality, it will change. It will change because of the observations. Let's think in D as the data set, I don't know, or yeah, the observations given our hypothesis or our parameter. And at the end, we will have a new reasoning that is called the posteriori value, that one in red color. So, well, we define already what a model is. So now we are talking about Bayesian reasoning that is old, I think, very old, but is still very useful and very popular. So the idea is that, well, this was before the machine learning revolution and the data science revolution. So the idea is that manipulating probabilities, we can make inference. So let's see this other formula. We want to get the maximum argument in the Bayes formula. So this is called maximum a posteriori. For example, from the step 2 to the step 3, do you know why we delete this term? You know, here is present, but not here. Can you tell me? Because there are like 20 formulas like this. No, just kidding. Well, we can see that this term is not affecting the other one, so we delete it. And also, if we have at all not prior knowledge, we can say that the probability of our hypothesis is the same, so also we can delete it. And we finish with this maximum likelihood estimation. That is a very important formula and is not so hard. So we will see maximum likelihood estimation in almost every algorithm. If you want to prove that your algorithm is correct, just try to match with this maximum likelihood estimation. And I will come back later. Oh, well, I just want to mention that there is a very nice paper where the paper studied the history of this maximum likelihood estimation. So it's nice, to see the progress. I don't remember the title, but you can Google if you are interested. So now we know more about some Bayesian reasoning, and we know that it's present in many algorithms, machine learning algorithms. So let's think on some problems with data. The data is always evolving. So for example, imagine Wikipedia the first years. I don't know how many articles or the topic of the articles, but let's say that they were just biology and chemistry, and then the next years, Wikipedia start to have articles in sports or biographies from artists. So the data was evolving. The same with the species in the planet. Every week or every few days, the biologists are discovering new species, so they need to modify somewhat the taxonomy sometimes, and then it's evolving the data. Let's think in the social networks. They are evolving every second. For example, the hashtags on Twitter. And well, how we usually address the problem, for example, clustering. There is a kind of common way to do it, one classic approach. So let's say that we want to use Gaussian mixture models. Let's think in the Gaussian mixture as something that is proven but the maximum likelihood. So the Gaussian mixture models is equivalent, not equivalent, but it complains with the, not complains, sorry. It fits with the maximum likelihood. This is a claim without proof. I won't prove it. But yeah, then in the Gaussian mixture model, there is bias reasoning. So yeah, we can do some clustering, maybe with Gaussian mixture, but then some question arise like, how many clusters do we need if my data is evolving? And then we usually create too many kernels and then do a comparison, I don't know, maybe with Bayesian information criterion or silhouette. There are a lot of metrics. And in this case, the best clustering was 5 kernels. I don't know if you can see. So this one, yeah, it seems a good clustering, but actually also number 3. So that is what we usually do. But let's think then in another approach. So we have seen the parametric approach, but let's think in a non-parametric approach. And non-parametric can be confused, like there is no parameters at all, but actually the number of parameters is infinite. But also there is a bad assumption about that. So the idea is that we have empty clusters, infinite empty clusters, and we will start to feed them with our data. So in this way, we can solve that problem if our models can be adapted to the complexity of our data itself. And well, let's see this diagram. So we have the Bayesian models. Some of them are non-parametric. And those names are funny. Like, you know, Chinese restaurant and Indian buffet. I don't know, sometimes the science is funny. You know, I am from Mexico. I am thinking that if I study enough the Dirichlet process, I can conclude another similar model. I don't know, the Mexican taqueria process, maybe. So these models are known as Dirichlet process, and I will explain the Chinese restaurant process because for me it's very intuitive. So imagine that we are in a Chinese restaurant, and usually the Chinese restaurants in California, I think, they are huge. So one scientist discovered that, and he said, oh, wow, the Chinese restaurants are huge, so you can go there, and if the restaurant is empty, you can choose any table. And then the second customer will go and will choose another table, or the same one with some probability. And then at the end, we realize that what is happening when a lot of customers are going to the restaurants is a kind of clustering, and each table is one cluster. And well, that's pretty cool. So that is the idea of the model, the Chinese restaurant process, one model that is evolving. So this is the clustering for the previous data we saw, but with the infinite Gaussian mixture model, that is some Dirichlet process. So we can do everything you can do with a parametric model. For example, digit recognition or topic modeling. And well, actually, I am in the conclusion part. So let's recap. In the traditional approach, oh, sorry, I mixed some letters. Instead of theta, let's think in probability of H. Well, the number of parameters are fixed. We have some distribution over those parameters. In the other case, the non-parametric models, we assume that we have infinite number of clusters, and our data can be adapted to, our model can be adapted to this data. So there are some libraries in Python, of course, Skylern, but they only have like 2 or 3 or one or two Dirichlet algorithms. And the best one, in my opinion, because it's more like in the research stuff, is this one, data microscopes. But I don't like it so much because they only are available on Conda and not in the official Python repository. But actually, yeah, they are the best library. They have the best library. So if we want to know more about this, we can study what the beta distribution is. In a nutshell, the beta distribution is just a probability of probabilities. And then we have the Dirichlet distribution, that is some generalization from beta distribution. Then that means that is a distribution of distributions. And finally, the Dirichlet process. Well, if you also want to read more about it, my favorite book in machine learning is the one written by Tom Mitchell. And this tutorial is really nice. And the library I mentioned, they have also very nice tutorials. You can check it. And well, that's all. Grazie.
So, have you questions? Okay. Can you use the microphone and speak directly to him?
Okay. So, you mentioned the Gaussian mixture model. Is that considered a Bayesian model then as well?
Maybe not strictly, but maybe the Bayesian model is not the Gaussian mixture model is not strictly a Bayesian model, but the algorithm that we use to do the clustering is expectation maximum, and this one use the maximum likelihood. So the maximum likelihood is derived from the Bayes rule. So yeah, somewhat we can say that is part of a Bayesian reasoning, Bayesian model. And actually there is some discussion, like most of what we know as Bayesian models, they are not exactly Bayesian models, but just statistical learning. And then let's think in that if we use calculus and we say for everything that we are doing things from Newton, and it's not exactly like that. Well, Newton was important in calculus, but there are other mathematicians that also put things in that, over that. So it's almost the same with Bayesian things. Sometimes it's not exactly Bayesian, but it has behind this Bayes rule.
Okay. More questions? So we have plenty of time. Have you questions? Okay. Seems. Oh, is there someone again? Oh, great.
Yeah, I can ask a second question maybe. So I'm just trying to understand this Bayesian models. Is it a category of models, or is it a like a way of using different other models? Because I mean, I know the name Gaussian mixture model, and I'm trying to understand Bayesian models. Is it also a category of other models, or is it a way of using a model?
Yeah, maybe. Yeah, there are some models that are strictly Bayesian. For example, let's say Bayesian networks. We have strictly some two probabilities that are not independent. That dependent. They depend on each other. So we can say that Bayesian networks are strictly a Bayesian model. And there are other ones, I think we can think on a Bayesian model for hidden Markov models, because yeah, we have some nodes and they have a dependency, and this dependency is a probability. But exactly, we can then discard Gaussian mixture model as a Bayesian model. But still, as I said, it has some Bayesian things inside. Very deep. I don't know if it was a good answer. Okay. So, well, maybe I can finish. Like, you know, I am more like software developer, but I am not doing software development anymore because it's kind of boring. Then I decided to do a master in computer science. I'm doing a lot of statistics now, but I am also not a statistician. So as Bertrand Russell said, I am not a philosopher, I am not a mathematician either, so I am a centaur. So it's the same.
Okay, last question. I don't see hands up, so thanks again to Omar.
Shall we start? So, how many of you know Booking.com? Hands up. Wow. So you probably know you can book a hotel, a room, an apartment on Booking.com. But can you book a container with a snake inside on Booking.com? That is the question. And Sahil Dua will tell us. Please welcome Sahil Dua. Warm. Thank you.
Hi, is this good? Yeah. So I will be talking about how we serve deep learning model predictions at Booking.com. And before I start, I would like to give a brief introduction about myself. So I would like to tell you what I am and what I'm not so that we have a better understanding of each other to meet the expectations. So I'm a backend developer working on developing the infrastructure for deploying the deep learning models at Booking.com. And I'm also a machine learning enthusiast, so both of these things just match well for me. And I'm also a big open source fan, and I'm a contributor in a couple of projects like Git tool that probably most of you have used already, and I'm contributing in Pandas library as well as Kintro by Mozilla, and GitHub project by Google, and a bunch of other projects. And I'm also a tech speaker. So let me talk about what I'm not so that we have the expectations at the same level. I'm not a data scientist, and I'm not a machine learning expert. So if you have some specific questions about how things work from a data scientist point of view and really about something related to deep learning or machine learning, I might not have the best answers right now, but I will be able to point you to where you can find the answer, or we can talk about that after my talk. So let me start with the agenda, what I'm going to talk about. I'm going to start with mentioning a couple of applications of deep learning that we saw at Booking.com. And then I will talk about the life cycle of a deep learning model from a data scientist point of view, like how this model looks like and what are the different stages of a deep learning model. And next I will talk about the deep learning production pipeline that we have built on the top of containers and Kubernetes. And yeah, let's begin. So starting with the applications of deep learning at Booking.com. The first application that we saw at Booking.com, so before I talk about the applications, I would like to talk about the scale, because I mentioned like we work at a large scale. We have over 1.2 million room nights reserved every 24 hours. And these reservations come from more than 1.3 million properties, which are across 220 countries. So we have this large scale, and this provides us access to a huge amount of data that we can utilize to improve the customer experience of our users. So the first application that we saw at Booking.com was image tagging. The question here is, what do we see in a particular image? Like, for example, if you see this image, what do we see in this image? And this is a really easy question as well as a difficult one. So if you ask this question to a person, to a human, it's easy because we know when we look at an image, we can identify the images, the objects in the image. And this is easy for a human. But when we talk about this question being answered by artificial intelligence, by machine learning or deep learning, it's not a very easy one. So for example, if we pass this image to some publicly available model, like ImageNet or something else, this is what we get. We get results like, so there are different classes: oceanfront, nature, building, penthouse, apartment, and all this stuff. But when we ask this question that what is there in that image, it really depends what context we are talking about. From Booking point of view, this is what we are concerned about. We are concerned about whether there is a sea view from the room or not, whether this photo is of a bed or not, if it's a photo of inside a room or not, or whether there's a balcony or terrace. So there are a couple of challenges associated with this type of problems. First of all, this problem is not just an image classification. It's image tagging. That means that there may be multiple labels, multiple classes for a particular image. And also, since our context is different from what other publicly available models may provide, we need to make sure that we come up with our own manual labels so that we can tag these images. And the next challenge is there is going to be a hierarchy of the labels. For example, if you see a photo of a bed, it may be of, so we know that if there is a bed in the photo, the photo will be of inside view of a room. Unless you are in such a room where there is no room, but there's only bed. So yeah, once we know that what is there in an image, we can use this information to improve the experience of the users. For example, if we know that a user is looking for a swimming pool in the property that they're going to book, we can show them, recommend or show them the hotel which we know that if there is a swimming pool, there is some photo which is tagged with swimming pool. Or similarly, if we know that there is some customer, based on previous history, that there is some customer that is looking for breakfast buffet, we can show the hotels or properties which we know have some photos tagged with breakfast buffet. So this way we can make sure that we are improving the experience of the customers and helping them find the hotels or properties that they want easily and quickly. Another application that we saw was recommendation system. So this is a classic recommendation problem. We have a user X. They booked user Y, hotel Y. Now we have a new user, user Z. We want to recommend some hotels that the user Z is more probable to book. So the problem statement here is we want to find the probability of one user booking a particular hotel. And what features do we have? We have some user features, which are like country and language of the user. And then we have some contextual features, like what's the day of the week when they're looking for it, or what's the season that they're looking for it, it's winter, spring, or what's the season. And the next set of features we have is item features, the features of the property that we are looking at, like price of the property, or the location of the property, or other information about that particular property. So once we realized that there are some set of applications where we could achieve better results using the deep learning, we started exploring this field, and credits to my colleagues Stas, Gherkin, and Imra, who is a data scientist, who actually started with exploration of deep learning on different applications, and now we are actually using it in production successfully. So next, let's talk about the life cycle of a model, what it looks like for a particular model from the start of the idea to when it actually is used in the application, in your applications, which may be anything. So these are the 3 steps: code, train, and deploy. In first step, what we do is, this is a step when data scientist writes a model, when they experiment with the different kind of embeddings, different kind of features, or different number of hidden layers, or any kind of that kind of approach. They test or experiment with different kinds of model architecture, and once they are happy with it, once they see good results, they move towards training on production data, and then they deploy. At Booking, we use TensorFlow Python API, which is a high-level API which provides easy to use functions to write a model architecture easily in Python. So when we talk about the production pipeline, these are the 2 steps that we have in the production pipeline that we call it: training of a model on production data, and the deployment in containers which can be served by any application. So you may wonder why training of a model is a part of our production pipeline. You may also use your laptops to train your models, right? But this is why it's not a good idea. So if you try to train your model on your laptop, this is what you may end up looking like. There are a couple of reasons for that. So one reason is your data may be too large that you can't use your laptop efficiently. Or another reason is that your laptop won't have, your laptop will, in most of the cases, will have limited resources. Will have some limited number of cores, or may not have a very powerful GPU. So these are the reasons why you may want to do the testing and experimenting with the model on your laptop, but then once you are sure that this is the model you want to go ahead with, it's a good idea to use some heavy servers or some specialized servers with GPUs or with a high number of cores so that you can speed up the process and speed up the process of deployment when you actually get the model ready. So this is how the training of a model looks like. We use our servers, like we have huge servers which have a lot of cores and sometimes GPU support as well. We wrap the training, so this is the training script for a particular model, and we run that on our huge servers, which are production servers. But there are going to be multiple data scientists who are going to train their models. And sometimes there are going to be multiple models being trained in the same, on the same server or on multiple servers at the same time. And we may not be able to provide independent environment if we do this in this way on a single server. So what we do is we wrap this training inside a container. So what is a container? Container is a lightweight package of software which you can run on a host machine, and it includes all the dependencies that your application may need. So we wrap this training script inside a container. We spawn up a container every time we want to train a model. And also this provides us easy versioning of the TensorFlow, because once we have a particular model written in TensorFlow, let's say 1.1 version, now the new model comes up and a new data scientist wants to use a new model, we can easily have that new container have the new version and use it. So basically, on the same machine, we are having different versions of the dependencies, and that's why we're using containers to make sure that we have these independent environments for all of these trainings. And also, it helps in the GPU support. We can also, these containers can also utilize the GPU support on our big servers that we have. So this is how it looks like. We have this Hadoop storage, where we have all the production data that we want to use for training our models. We spawn up a new container when we want to train. It has a training script, and it fetches the data from the Hadoop storage. It runs the training. Once the training is done, we want to make sure that the model checkpoints, the model weights are stored somewhere so that we can utilize them later in production when we deploy them. So what we do is we save the model checkpoints back to Hadoop storage, and the container is gone. Yeah, so it's like, what can be more selfless than a container? It takes birth to do what you want it to do, and then it dies. So that's the entire life of a container. So once we have this training done, we have trained our model on production data, and we have stored the model checkpoints on Hadoop storage, which we can utilize now. Now, deployment is putting that model in production somewhere, in servers or in somewhere, where you can utilize that model to have predictions by your different applications that you may have. You may have your web application, or you may have your app, Android, iOS, any app, and you want to make sure that you can utilize those, that model from those applications. So what we did was, we have a Python app, which is a basic WSGI HTTP server, where you can, what it does is, it takes the model weights from the container, from the Hadoop storage, and it loads the model in memory. So when we want to load a model, it needs two things. It needs the model definition, as well as the model weights. So we have the model definition already when we have this Python app running, and we get the model weights from the Hadoop storage. We combine these, and we load the model in memory so that it is ready to serve the predictions now. And on the top of this, it also provides a nice URL, a nice, easy to use, easy to remember URL to get the predictions. So basically, it all boils down to sending a GET request with all your parameters that you have, and getting the prediction back. This is how it looks like. Again, we have this app running in a containerized environment so that it's independent and it carries all the dependencies with itself, and there's no problems like it runs on my machine or it runs on this version of OS, it doesn't run on that version. So it contains all the dependencies that it needs, and it can run on any server where you can run Docker containers. So basically, we use Docker to manage, to use the containers thing. So this is how it looks like. we have the containerized serving of our model, and we can have any kind of clients which will just send us the input features and get back the predictions. But as I mentioned earlier, we have a huge scale that we operate on, and when we have thousands of requests or millions of requests per second, we can't just have just one server. So what we do is this. We spawn a lot of containers, put them in behind a load balancer, and the client doesn't know how many servers are actually serving. You just send requests to a load balancer IP, and load balancer takes care of all the scheduling, all the rerouting the request. Since we have huge, large scale, we have plenty of more containers. So once we keep on increasing the number of containers that we have for one application, we want a way to be able to manage these containers, because it's possible that sometimes we want to increase the number of containers, or sometimes we want to decrease the number of containers when we see that there's less traffic, or also we may want to diagnose some of the containers when something goes wrong with the containers, or let's say we want to kill some of the containers and spawn them again because there's some error or something. So for this, we use Kubernetes. Kubernetes is a container orchestration platform which helps us in scheduling, maintaining, and scaling applications using containers. So Kubernetes is a really nice tool by Google, which provides us a really nice flexible way to scale up or scale down any application at any time. We can create new instances, new containers, put them behind the same load balancer, and those containers will be now serving the applications to the request from the clients. Or we can scale down easily with just one command. And also Kubernetes makes sure that if we mention that we want to have 50, let's say for example 50 containers for application, it makes sure that even if one of the containers or two of the containers, or let's say 10 containers die because of some error, it makes sure that at any moment it's going to retry and create new ones, so that we don't have to care about if something goes wrong unless there is something seriously wrong and it can't create new containers. So basically it will try to maintain the number of containers to a particular limit that we have set. So once we know that how we deploy the models, we also need to be able to measure the performance of these models in production when we have a lot of requests coming in at a rate of plenty of thousands of requests per second. So this is how it looks like. Let's say you have your model, and it takes some computation time to compute the prediction for a set of features, for a set of input features. But that is not going to be the time that your client is going to see. Your client is going to also have some request overhead because of networking latency, depending on where your app is hosted and where your client is coming from. So this is how it looks like. The prediction time total is sum of request overhead and the computation time. And if you have n resources, you just, if you have n instances you predict in one request, you just multiply it by computation time, and this is what you get as a rough calculation of your prediction time from client point of view. And we can see that if we have some simple models where computation time is like simple models like logistic regression or linear regression, where we have a small set of features and it's a small model, there we will have the request overhead will be the bottleneck, and the computation time will be almost negligible compared to the request overhead. So once we know this is the kind of performance that we can expect, there may be two things. Either you may want to optimize for latency or throughput. Let's talk about latency. Latency is the amount of time it takes to serve one request. So how can we, you may have some applications, like let's say you have a web application which needs to be served as soon as possible, so you want to optimize for latency there. And these are some of the ways that you can use to optimize for latency. The first way is don't predict in real time if you can pre-compute. So this is a simple way when you can pre-compute all the results that you know that are going to be there to predict. You can just save them in the lookup table and serve from that lookup table, and you will be really fast, and you won't have any computation time in the real time. But we understand that it's not always possible. In most of the applications, we have the need to predict real time. what we can do there, we could reduce the request overhead. And one of the ways we could do that is we can have the model embedded in the application so that there's no latency in accessing the model and getting the predictions back. So that's what we do as well. We keep the model in memory in the container that is serving the app, and so that it's able to predict and return the request quickly. Next is predict for one instance. This is useful when you have computation time, which is huge as compared to the request overhead. When you know that your computation time is the key, is a bottleneck for your request, you should send as many requests as instances you have. So let's say you want to predict for 10 set of instances, you should send 10 requests because you know that your request overhead is not the bottleneck here, and you don't want to reduce the request overhead. You just want to make sure that you've sent requests as soon as possible and get the results back. And you can also do some techniques like quantization, and what that means is it means you convert your float 32 values to fixed type 8 bits, and how it helps is that now your CPU can hold 4 times more data in the same processor, and hence it becomes faster in processing that data in computing the float values as compared to computing the float values. And there are some TensorFlow specific techniques like freezing the network. Freezing the network means that when you have some computation graph, what you do is you have some variables, TensorFlow variables, and if you convert those variables into TensorFlow constants, you get some boost in the performance and the speed of the computation of the predictions. And another thing is you can optimize for inference. What that means is you can remove all the unused nodes from the graph, and that will help in boosting up the computation again. Next is we may want to optimize for throughput. Throughput means the amount of work being done in 1 unit time, maybe 1 second, 1 minute, depending on what your use case is. If you want to get a lot of work done per unit time, it's again, the first thing always is do not pre-compute. If you can always have a lookup table with all the computations and use them when your request comes. And another thing you can do is batch the request. When you know that you want maximum amount of work done in a unit time, you want to reduce the request overhead as much as possible. So if you send a lot of requests together in one request, let's say thousands of requests, you're going to get performance boost of those 1,000 times request overhead, which you don't have now as compared to when you could have sent those requests one by one. And you can also send parallelized requests. And you can just use asynchronous request instead of using instead of waiting for one request response to come back before sending another request. You can just send them all in parallel and let the servers do its work and asynchronously collect the responses and make sure that you get maximum work done in unit time. So let's try to summarize what we talked about. First of all, we talked about training of models in containers. We spawn a new container. It fetches the data from our Hadoop storage. It can be MySQL as well. It really depends on the application. And it runs the training script in an independent environment in a container. Once the training is complete, make sure that it stores the data, stores the model checkpoints back in the Hadoop storage, and it dies. That's the entire process of the training of a model in container. The next is serving these models from containers using Kubernetes. We spawn as many containers as possible, as we need, depending on how many requests we have for that particular application. And we let the Kubernetes do its stuff with the load balancing as well as maintaining and managing the containers and providing us an easy interface to diagnose all the problems that we may have. And the next is we optimize these serving of apps used for latency or throughput depending on what the application is. If you have like cron job or something which has a lot of work to do in one burst, you can use the techniques to optimize for throughput. Or if you have real-time application in which you just need to show the result right away to the user, you can optimize your serving for latency. We have both these options available in our pipeline. To work on all these cool things, and a lot of other things like MapReduce, Spark, recommender systems, and a bunch of other things we are hiring. We're hiring especially for software developer roles as well as data scientist roles. So yeah, if you want to, if you're interested on working on these things, you may check out this link, or you may get in touch with me on LinkedIn, Twitter, or GitHub. I go by Sahil2305 name on most of the social media websites. That's it. Thank you.
Thank you, Sahil. Please raise your hand if you have a question.
Hello, thank you. So you use Kubernetes and you can scale up and scale down number of replicas, right? As you mentioned it. What do you use to decide whether you should scale up replicas or scale down? Like what algorithm, what is behind the load balancer? Do you do it manually or automatically?
I didn't understand your question. So what do we use as a metric to decide whether we want to?
Yeah, exactly. Like you have number of replicas, like 5. Now you have load, and you want to decide if there should be 10 replicas or scale down. You know.
Mm-hmm. Yeah. So Kubernetes out of the box provides us support to a few metrics like CPU usage, disk memory, as well as the traffic that we get like in the number of requests. So it really depends on the kind of application that we want, because in some of the areas we want to have the metric CPU usage, which tells us how busy are our CPUs on the particular container, or we may also want to use the WSGI queue size, because once we have a lot of requests coming to containers, we want to make sure that those queues are not full. And once those queues are getting full, we want to spawn more containers so that that traffic maybe can be distributed so that those queues are not dropping off the request. So it really depends. WSCI queue size is one of the metrics that we are looking at.
Okay, thanks. And my second question is, how do you annotate your data for model training? Do you have some team of annotators, or how do you do it?
Your question is, how do we come up with this data, or what?
How do you annotate data, like the images? If you have some team of annotators who draw, this is bed, this is chair, this is window.
Oh yeah, okay. So when we started writing this model for image tagging, we outsourced this tagging manually. We had some huge number of images which were tagged manually by people, by humans, and we used that data to train our model.
And it's some company, or how did you hire them?
Sorry?
It's some external company that has these annotators, or how you made it?
Your voice is not clear, sorry.
Oh, I will come after the lesson. Yeah, thanks.
Yeah.
Okay, so thank you very much for your talk. I think this is one of the main problems with Python and machine learning, deploying it. I would be interested, if you want to use machine learning, you usually have to do some feature engineering, like you get some input data and then you have to crunch some numbers. Where do you actually do that? Do you do that in the app and you tell the app, okay, you have to provide this data? Or do you do that in the container? Or do you do it on the Hadoop when the data comes in and you just kind of like send a pointer to the Hadoop data?
Yeah, so that's something that I didn't cover. So what we do is we have some kind of events data that is being logged in all the activities that we have on our website. And once we have the data, we have some Uzi workflows or cron jobs which deal with that data and prepare that data to the kind of data that we want to use in our models. So we have separate workflow which takes care of the data munging and preparation of data basically for these models.
I was wondering if you could talk a little bit about how you iterate with your models, and let's say, I'm not sure whether that's the case, but if you have some new training data, you want to take it into account, you want to retrain your models and then check whether they're still performing well or not. How do you deal with these kind of things?
So are you asking about how we deploy new models or the performance testing of new models?
Both.
Okay. So once we know that we have new models, we want data scientists want to update the model. What we do is we have some particular. So we use OpenShift on the top of Kubernetes to manage the graphic interface of the entire structure. So once we know that there is a new model, we update our deployments with that new model, and we can use A/B testing to see what kind of results we get, and we have proper monitoring which tells us what's the distribution of our feature sets, what's the distribution of our outputs for a particular model, and we can use that information to decide whether the model is good or not, whether we want to keep it or move to the previous version.
In your talk that one of the ways to improve throughput and latency was to cache or to have a hash table of previous predictions. How do you implement that per container, or do you have a centralized, and what technology do you use for that?
So the thing that I mentioned for caching and keeping the predictions in the lookup tables, that is something that really depends on your use case. So honestly, we haven't found out that kind of use case where we already know what kind of predictions we are going to predict. So what we do is we don't use the lookup tables, but we predict in the real time. So we use the other kind of techniques that I mentioned to optimize for latency as well as throughput. So we don't already have some application where we could employ the lookup tables.
Okay, so that's it. Thank you, Sahil. Please give a warm round of applause to Sahil. everyone. Shall we start? So I've got a question. What do you call like when you have an area of high pressure and low pressure? What happens in between? Airflow. We're gonna be hearing about airflow. Okay, please give a warm welcome to Michał Karzinski.
Hi, can you hear me? All right. Thank you for coming to my talk. It's going to be on airflow and workflows. But first, just a few words about me. I'm Michał Karzinski. I work with Python, but also with JavaScript and with Linux. I also write a blog, which some of you may know, and I'm currently a tech lead at Intel and also a consultant at a company called Aptaria. All right, so let's talk about workflows. How many of you know what I mean when I say workflow? Raise your hands. Okay, that's like 4 people in the room. So it's a very vague term, but it's a popular word also. So it can be very confusing when I'm just saying that I'm going to talk about workflows. So I'm going to define them a little bit to narrow down what I mean. When I'm talking about workflows, I mean that we have a sequence of tasks that are started on some schedule or maybe triggered by an event happening somewhere, and these will carry out some work for us. This is frequently used with data processing pipelines and other jobs in the big data field. A typical workflow could look something like this. I get some data from some data source that came in, and I'm downloading it for processing. Then I'm sending it off for processing on a system somewhere else. Then I have to monitor whether the processing was completed successfully and if it's done. And when it is done, I get the results of the processing back. I generate a report, and I send this report out by email to some people. So that's a very typical workflow example. But this workflow methodology is so generic that there are examples almost everywhere. So many types of ETL workflows could be defined. Data warehousing is also a place where you would use a workflow. You could use a workflow when you're doing A/B testing to handle some of the automatic steps for you. Anomaly detection is another area where workflows are used. Training recommender systems that were just presented in the previous talk are probably using some workflow system to get this job done. Orchestrating automated testing. This is actually what we are using Airflow for at Intel, so that's why I marked it there. And another example from bioinformatics field, you could be processing some genome every time a new genome file is published somewhere. So all of these jobs could be handled by a workflow. Because of this, a whole slew of new workflow managers has started to come up in recent years. And there's these, which are listed on the screen, these 5, are just a small subset of all of the ones that are available. And these are the more well-known ones. But I will be speaking today about Airflow. And Airflow, or Apache Airflow, is an open source project. It's written entirely in Python using some well-known Python open source technologies itself. So it's based on Flask and uses Celery. It was originally developed by Airbnb, but it's grown very quickly and extensively over the last couple of years. So it currently has almost 300 contributors, 4,000 commits, and many, many stars on GitHub. And it's used by hundreds of companies. We're using it at Intel. I guess Airbnb uses it, and Yahoo, PayPal, and many others are using it also. The Airflow provides you with 3 things. It provides you with a framework for writing your own workflows. It provides a scheduler and quite a scalable executor for running the workflow tasks. And it also provides a web UI for monitoring the workflows as they are running and for viewing logs. So in this talk, I will focus primarily on this first point, on the framework which you can use in Airflow to define your own workflows and tasks. I won't be speaking very much about the executor or the scheduler, but there already was a talk on that this morning, a good talk by Federico Mariani, who was speaking about Airflow also. So if you missed that one, I'm sure you can find it on YouTube later. All right, so before I begin showing you code examples and other things, I will take a minute to show you Airflow itself, give you a demo. So when you set it up and run Airflow on your computer, you will get this web interface to it. So it lists all the workflows you have defined in a table, and if you click on this little play symbol right there, you will be able to start a workflow manually, just like that. And then you can go in and take a look at your workflow. This one is called Hello World, and you will see that it's currently being executed, it's running. This task already managed to complete. This task is going to be scheduled in a second. And you can see the whole history of your workflow's runs. And for each of them, for each task, you get an entry in this table. You can click on it and view the logs of a particular task. If any errors occurred, the logs would be here. You can click on a graph view, and then you will see another view of the same workflow, from which you can also view its logs. So my Hello World example returns Hello World, so it works. So that's the UI. And it's actually very easy to get to this point. Installing Airflow and setting it up is quite easy, but I will be talking more about the code needed to write workflows in a second. But before I do that, I want to talk about what actually flows in a workflow. Why is a workflow actually called a workflow? So every task that we have in our workflow makes decisions, and those decisions are based on the input to the workflow run that was started, and also the output of upstream tasks. So all information flows from downstream to from upstream to downstream. So it's kind of like a river, and I want you to think of a river for a minute. Like a river, a workflow begins somewhere. So it has a source. It may have many tributaries which join together to form this river. It also ends up somewhere, like a river flowing down into the sea, or it can form many final branches like a river delta. What a workflow also does is it can have branches. So, okay, this is where the analogy breaks down a little bit, because rivers don't usually do that. But workflows do. They can have very many branches which can split up from the main branch of the logic of the workflow and then join back together to form the final workflow result. So this isn't really a river, it's a graph. It's a directed acyclic graph, so where the information always flows from upstream to downstream. And you can actually use that very creatively when you're designing your workflow. Because if you put some information into your workflow at any point, it's like putting a message in a bottle into the river at some point. It will flow down and pass every point. Well, I guess you would have to put many bottles into the river if you wanted it to reach every point, but the point is you can put information upstream and it will flow downstream. So if I put some information at point B, it will be available to all points in the graph downstream of that. If I put some information in point D, the same thing happens. And then finally, at this end point where all the branches combine, I get all the information and I can generate my report or do whatever I need to do with all this information. So when when you're writing your workflows with this in mind, you can make them quite modular and make them use information from sources upstream in the tasks that are running after that. Okay, so that's enough about rivers and about the magic of the graphs. Let's get to Airflow and how Airflow works with this. So Airflow uses the concept of the directed acyclic graph for all workflow definitions. And that allows you to define the logic of your workflow as the shape of the graph. And this is very easily done. This is actually a complete code example of the Hello World workflow that I was showing at the beginning, aside from missing some import statements. So I'm going to walk you through these couple of lines, but it's very simple. So first of all, there's some Python function that I want the workflow to execute. This one just returns hello world. And then I define the DAG just by specifying a couple of parameters. And using that DAG as a context manager, I define a couple of tasks by instantiating these operators. So first one is called dummy operator, second one is called Python operator. But these create tasks, and in order to combine these tasks into a graph, I can use this bit shift operator that was overridden to allow joining tasks together. So this method of defining graphs is very quick and easy, and when you get used to it, it allows you to create graphs as complex as you need. And moreover, since this is being defined in Python code, you can use any looping logic that you want to define more complex graphs. The next Airflow concept I want to talk about is the operator. This is the way you define the actions of a single task. An operator is essentially a Python class with an execute method, and that's all you have to create to have a very robust entry in your graph and in your workflow, because this will automatically be retried, and if it fails, it can be repeated until it succeeds. And therefore, each of these functions should be idempotent so that if it runs multiple times, it won't have unintended consequences. But an example is just this simple. In fact, I made this slightly more complex than it needs to be, because all it needs to be is a class with the execute method. But I added this one parameter up there to show you that you can also parameterize your tasks by in the definition of the DAG when you're putting them in the final DAG by passing parameters through the init function. Another concept Airflow uses is called sensor, and sensors are long-running tasks. This is very useful for monitoring purposes. So if you have some data processing job running somewhere, you may want to check on it periodically to see if it finished. And Airflow gives you the ability to do this very simply if you define a sensor class with a poke method. The poke method will be called repeatedly until it returns true. So a very simple example is this one. I have a sensor with a poke method, and this one, this example is slightly silly, but it just checks if the current time, the minute, is divisible by 3. And if it's not, it returns false, which means that the method will be called again after a certain number of time. I think it's 1 minute by default. And until it returns true, it will be called again and again. And then finally, when we reach the point where the current minute is divisible by 3, we will return true, and the sensor will exit. Another very important concept in Airflow is XCOM or crosscom. It's a means of communicating between tasks. This is just actually a way to save things in a database, a simple way to save things in the database and then retrieve them later. So because these things, these messages that you pass are saved in the database as pickled objects, it's best suited for small pieces of data like object IDs rather than whole objects, but it works very well when you use it this way. So it's very easy to use. In your operator, in your task, in the execute function, you have a parameter called context, and if you just retrieve the task instance, the running tasks instance from this running execution context, you can call the xcom push function to pass some information into crosscom. And then in another task downstream of that one, you can call xcom pull to retrieve this information and use it later. You can also do a trick for scanning all upstream tasks by using something like this code example, which has these 3 lines in the middle here, where I'm getting all the upstream tasks from the graph, and then I'm calling xcom pull on all of the IDs of the upstream tasks and querying all the upstream tasks for a specific piece of information, and I get an array of all the defined database IDs in this case, for example. What you can do when you're defining your workflows with Airflow is actually create reusable operators. And this is what makes Airflow workflows very modular. Because if you use loosely coupled functions as your operator functions, meaning that you have only very few necessary parameters passed in by XCOM, and most other parameters are optional and have same defaults, then you can put an operator like that, a task like that, in very many different types of workflows. So in this example, I have a pink operator called Nexus, which can be something that collects information from a lot of upstream tasks and combines it somehow. But it can also be used in a different place, in a different graph, where it doesn't have all the same information coming from upstream, but it knows how to behave well in that context as well. And it plays a slightly different role in another workflow. So this proved to be a very powerful technique for us when we're doing our test orchestration using Airflow, because we're defining like blocks of code which fit in many different places, and we're able to combine them into very many different workflows by reusing the same components in different contexts. So if you pay attention to these details, you would be able to do the same thing. So let's look back at the typical workflow that we started with. The tasks that are part of the workflow are defined in Airflow through the operators. The one that's used for monitoring processing is a long-running sensor, and all information that passes from upstream to downstream tasks goes through this cross-com functionality. Okay. There are some more interesting things that you can do also. For example, if you want to follow a certain branch of the graph and skip others, you can use an operator called the branch operator, or the branch Python operator. So that's a very simple example up there. You have a graph with three tasks, one upstream and two downstream, and then the upstream task, the branching task, decides which task to follow simply by returning the ID of the task downstream that needs to be executed. all others will be skipped. Another way to skip tasks and therefore maybe skip entire branches of your workflow that you don't want to execute is by using a special kind of Airflow exception called the Airflow skip exception. And this exception will force this particular task to be skipped, whereas all other types of exceptions, if they're not caught, will cause the task to be retried. And if the retry doesn't ultimately work out, then they will fail. So this skip exception is like putting a dam in the river. You're stopping the flow of the workflow downstream, but you can actually control whether you're really stopping or the execution by deciding what trigger rule your your particular task has. So by default, all tasks require all upstream tasks to be successful, but you can change that to a different one of the options listed up there, and the one that I find particularly useful is all done, which means that whether a task succeeded or failed, your downstream task will execute. And if you write your operators in such a way that they know how to behave even when the upstream failed or was skipped, then you can continue the execution through your workflow going downstream. So all done is like opening the dam from downstream of the task. You can do a lot of other very useful things with Airflow that I'm not going to get into the details of, but for example, you can run bash commands as your tasks. So in order to execute bash commands on a worker, you can use the bash operator, which allows you to pass in a bash script, which is actually wrapped in a Jinja template. So you're actually running a bash script generated by a Jinja template. I guess an example is worth more than a lot of words. You can put a template into the bash operator, and this will be first executed, and then the bash command will be executed on the worker. So Airflow also allows you to write a lot of plugins, to extend it. So writing plugins is also very simple. You just create a subclass of Airflow plugin and put it in the plugins directory, and then you can define a whole list of things that Airflow uses and make them available to your instance of Airflow. So operators we already talked about, but you can also define menu links for the web interface that I was showing at the beginning. You can create whole admin views because it's based on Flask admin, so you can create additional views in the administrative interface, or even entire Flask blueprints that you can plug in, and it's actually very extendable, so I'm sure it will be useful for many cases that you may have. All right, that's it from me. There's a tutorial available on my blog, so if you want to get started quickly with trying Airflow, go there, and thank you very much.
Thank you, Michał. If you have any questions, please raise your hand.
So I wanted to ask, how does Airflow integrate with distributed systems? So if you want to distribute your process, for example, you run some method and you actually want to distribute it over multiple servers, how can you then, because you trigger like an execution of that process with Airflow, so how can you then decide that it, for example, not runs on your local machine, but then on a different server somewhere else?
So the underlying technology that we're using for distributing work along different workers is Celery, and Celery gives you a lot of control over where things get executed, so that would be one way. Other than that, I guess it would be more manual than automatic. But we didn't actually have to make these decisions because all our workers are capable of running the same set of tasks. So not going to give you a definitive answer, but celery is under there, so going that way would work.
Hi. I have two questions actually. The first one is like, is it resilient? Is it like, do you use it in production at the moment?
Yes.
Okay, and do you have any use case for sensors?
Yes, we do, because we are actually, like I mentioned, we're using it for orchestrating automatic testing, and these tests can run for a long time. So we're actually checking on the executors, which are not the same as our Airflow workers. Our Airflow workers are just the ones who trigger the tests, but we're checking on the executors if they finished running all the tests, and when they're done, then we can make some decisions about what to do next. And sensors work in that context quite well.
Great talk. Thanks for that. Two questions I have is, do you run Airflow in more than one node? And the other question is, have you seen Airflow being used to tasks that require manual input?
I'm not sure I heard you correctly. Could you?
Okay, so yeah, the first question was, do you run Airflow in more than one node? Like, can it handle the workflow being run in more than one component, more than one node, more than one server?
Mm-hmm.
And the other question is, have you seen or have you ever have the experience of running Airflow for tasks that require manual input, some user input?
Okay. So first question actually has a good answer, because we are running a triplicate of servers. So we have 3 web interface hosts, 3 worker hosts, 3 schedulers, and without actually having to do very much, Airflow was able to behave very well in this context. So it was running in parallel on 3 different servers. All 3 services were running together, and they are able to exchange information. So when I click to view logs on the web interface, it's able to pull the logs from the correct worker. It knows where the logs are. So it's able to work on multiple nodes like that very well. In terms of manual input, to do that, we had to create an API that has that will have a user interface, but through that API, we're actually calling Airflow's methods for starting some workflows with additional input from users. That is not something that comes out of the box, but we were able to extend it by adding some API methods to the administrative side.
Okay, thank you for the talk. It was very interesting. One question that would be very useful for a project of mine is, can you actually group the operators and reuse the groups?
When you say you want to group them, do you mean you want to group them logically, like in a class hierarchy, or group them into smaller workflows?
Now, for example, if I always use the same 5 operators in the same configuration, then can I put them into one overreaching operator somehow?
So there is an operator type that I haven't experimented with, and I'm not sure how well it works, but it's there for this purpose. It's called a sub-DAG operator. So you create like a DAG with a bunch of operators, a graph of the 5 operators like you were talking about, and then you use that as an operator itself. So you kind of put the whole graph into another graph. But I haven't used that, so I'm not sure how well it works.
Okay, thank you so much. Thank you, Michał. Please give another round of applause to Michał.
All right, welcome to the last session of the afternoon. Okay, 3:45. We are going to have Julien here talking about artificial intelligence on our Raspberry Pi. Please welcome Julien.
Thank you. Thank you. Can you hear me fine? Yes, sounds like it. Okay. Well, it's been a long day for you guys. It's been a long day for me. Flying very early this morning from Paris, but it's good to be here. I hope you have some energy left. It's a longer session, and so we will have plenty of time. And I suggest if you have any questions during the session, please ask your questions. Please raise your hand, and we have a microphone somewhere that you can grab and ask your question, okay? I'd rather have a more interactive session than just wait until the end and answer questions on stuff I was talking about 34 minutes ago, okay? So please raise your hand and ask all your questions. So my name is Julien, or Julian, or Giuliano, or whatever you want to use, that's fine. I'm a tech evangelist for AWS. I'm based in the Paris office sometimes, because most of the time I'm really traveling and talking to developers and like today, and that's fine. I've been with AWS for about a year and a half, and before that, I've spent the last 10 years or so as a CTO and VP engineering in web startups in Paris, okay? So indeed, today we're going to talk about artificial intelligence, and I'm going to take you on that long journey that started in the 50s, and if everything goes well, we'll end up running some stuff on my Raspberry Pi robot, which is waiting in the shadow to exterminate us all, maybe, who knows, and we'll see what we can do with this, okay? So I'll start with a very quick introduction of AI and why it's been mostly frustrating so far. And then we're going to talk about Amazon AI, what do we do at Amazon and AWS. And fairly recently, we've had some new stuff coming out. And then I'm going to talk about, and the most of the presentation actually will focus on an Apache project called MXNet. Who has already heard of MXNet? All right, well, okay. I'm progressing. Usually it's 0 people, which is why I'm talking about it. So MXNet is a deep learning library, which is extremely developer friendly. It's really designed for quick experimentation by developers and by non-experts, right? So I always say you don't have to have a PhD to use MXNet, and that's fine. That's exactly what we want to do. So we'll talk about MXNet for a minute, you know, the high-level features and so on, and then, of course, we'll go into some demos using Python code. What a surprise, right? I can show you some other code if you want, but you're going to throw stuff at me, right? So it has to be Python today. And then, of course, I'll point you to some more tools and some more resources to get you started. So the story so far, well, that's it, right? So who has no idea what this is? It's okay if you raise your hand. All right. Okay, so thank you for making me feel very old. Yeah, I keep thinking some people in the room are older than me, but as time goes by, this becomes false, you know, all the time. So this obviously is from the Stanley Kubrick movie 2001, A Space Odyssey. If you haven't seen it, you have to see this. It's a masterpiece, and it's the first visual representation of artificial intelligence. It came out in 1968 or 1969, and this computer is inside a spaceship, and it's really running the ship, and the astronauts, you even wonder why you have astronauts in there, which is probably why the computer decides to kill them eventually. So you know the end, but you should still see the movie. And I guess a lot of geeks like me and computer scientists and researchers have been obsessed with this, you know, when we first saw the movie. This is what we're trying to build, right? This is the ultimate artificial intelligence that can understand natural language, that can speak, that can handle very different and very complex tasks. You know, imagine driving a spaceship. You know, how complicated is that? So this is basically what people have been trying to conceive and build over the years. And, well, have they succeeded? No. And actually in 2001, the real year 2001, a famous computer scientist called Marvin Minsky, is one of the fathers of artificial intelligence. He founded the AI lab at the MIT and did plenty of other things. And actually he was an advisor to Kubrick on the movie, right? So he worked with Kubrick in '68 to design what HAL would look like, right? So pretty funny. And so in 2001, Minsky wrote a paper, said, it's 2001, where is HAL? And, well, obviously nowhere. And it gave a number of reasons why artificial intelligence had not made a lot of progress in 40 or 50 years, right? And he thought we were still very, very far away from having HAL. And I think it's a paradox because in the mid-2000s, machine learning started to explode, right? And now today, everybody, who's doing machine learning in the room? See? All right, okay, thank you. Everybody, right? All right, at least everybody has machine learning on their resume, and that's fair enough, right? I have it. It's a commodity. It's easy to do machine learning. You can get some open source libraries. You can grab in, the scikit tools in Python and build machine learning models in just a few lines of code. You can use cloud-based services. You can use, you have a wide choice. So, why did machine learning become so successful starting in, 2000 until, 2010 and now even more so? Why did this make a lot of progress, and why did AI not make a lot of progress in the same years, right? Well, it's because, as you know, in machine learning, it's all about the features, right? So it's fairly easy to build a prediction model, provided that you have clear features. And actually, most of the work of data science is to find what features are useful in the data set. How to engineer them, how to prepare them so that they can deliver a nice, efficient working model, okay? So let's take an example. If you have a web log, Apache log or something similar, and you want to use those logs to predict user activity, it could be predict what link they're going to click on, what ad they're going to click on, etc., typical activities, then all the features are pretty much available, right? You just look at what the log has, and the time and date, and URL, and user agent, and blah, 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 and probably 50 more. And you just have to figure out which ones, a user ID, obviously, and you have to figure out which ones are the ones that are the most relevant for your machine learning model, okay? And you go and tweak them and combine them and twist them into form until you have a working model. Now, let's take a different problem, okay? Suppose I take a picture of this room, 1,000 pixels by 1,000 pixels, and I want to know who's in the room, or what's in the room, or is that even a room? I want to know what the picture is. Okay, so it's 1 million pixels. And if it's a color picture, it's likely that it's actually 3 million pixels, right? Red, green, and blue. So does this mean I have 3 million features? Should I take those 3 million features, flatten them and send them into a prediction model? Would that work? Probably not, right? I'm sure some people have tried, but that's not really working. And if you think about it, does it even make sense, right? Is every single pixel in this picture useful information, right? Look at the seat you're sitting on. I mean, it's all gray and it's all the same color. So do I need all those individual pixels to figure out this is a seat and it's gray? Again, probably not, right? Common sense tells me no, I don't, okay. But that's the difficulty in building those smart applications, right? Common sense, human common sense, tells us the answer immediately. If we brought a 5-year-old kid in this room and asked, okay, what do you see? He said, well, I see people sitting in a room. So it looks like a classroom maybe, right? And if you show animal pictures to that kid and say, okay, is that a cat, is that a tiger, is this a dog? He would know instantly. Okay, but if you ask that kid, okay, how do you know it's a lion and how do you know this is a cat, right? Then it becomes more complicated. Okay, and he would give you some answers, right? But how do you fit that into data that a computer can understand? And that's the number one problem with deep learning, right? And this is the problem that deep learning is actually trying to solve. It's trying to teach computers to understand informal things, right? Things that you and me know pretty much, from 4-year-olds, from being 4-year-olds and older, but it's impossible to teach a computer to do this. Okay, so if you try to do it the machine learning way, it doesn't work. Okay, because there are too many features, there's just too much information, and you cannot feed all this information to a machine learning model and get a decent result. So, of course, the answers to this is neural networks, and they're not new at all. They've been around for decades. The early work even goes back to the late 40s, but the first major applications came in the 50s, right? So it's literally 60 years old technology, right? 60 years old. And what is a neural network, actually? Well, people have written books about this. I've spent their life explaining this, so I'll keep it shorter and simple. Basically, a neural network is a universal approximation machine. It's the name of a theorem that says that if a network is large enough and if you give it enough data, it's going to learn anything perfectly, right? That's it. So it's a learning machine. It's a learning machine. You design it, you show some data over and over and over again, and it learns perfectly how to predict a given output from a set of given inputs. Okay. It can predict absolutely anything, and magically. You don't have to understand exactly what happens in there, which is nice. But, okay, mathematically, they're great. Theoretically, they're great. For limited applications, they were great. But, until very recently, they didn't really work, right? They didn't really work. And if some of you, the older ones like me, were in the university, let's say in the 90s, and you studied, probably you had a few hours on neural networks and AI. I'm sure your teacher told you something like, well, yes, okay, artificial intelligence is really cool, neural networks are really cool, you can do all kinds of crazy stuff on paper. But, outside of the lab, they're pretty much useless because we cannot solve bigger problems with those. So it's all about scale, scale, scale. So that's it. That's the reason why they didn't work. That's the reason why in the 60s and the 70s and beyond, they just stayed in the lab, and they were cool stuff to play with, but there were no industry applications, no real-life applications of these, because data was just not available. Okay, and remember I said you need lots of data to train, and computing power was not available either, right? So, tough luck. But it changed. Right? It's changed for 3 reasons. The first one is data sets are everywhere, right? Digital data is literally everywhere, okay? Audio, text, pictures, everything. Some public data sets are available on the internet, large ones. You can grab them, you can mine them. You can go on Kaggle, you can do machine learning competitions, deep learning competitions. So data is just everywhere. So everybody now can grab data and start training and start building apps. The second thing is computing power is, well, it's always a problem, isn't it? It's less of a problem than it used to be, right? Because now we have GPUs, and in the mid-2000s and later on, research teams found that actually GPUs could be used for something smarter than playing 3D games, right? So instead of using all that fantastic power to build 3D games and shoot each other, well, we could, do some actual scientific work. And, I guess that's the good thing. And so now GPUs are everywhere. They're fairly cheap, and they deliver massive amounts of computing power. And the third thing that helped deep learning explode is the elasticity and the scalability provided by clouds. Okay, because just like everything else, why would you buy 50 fancy GPUs to train for a couple of hours a week and have them do nothing the rest of the time, when you can just go to the cloud and grab a few GPUs for a few hours, train your model, and pay for those few hours and release them, right? So the elasticity, the pay-as-you-go, everything that you know for cloud also applies there, right? Compute, storage, etc. It's all there. Grab it, use it, release it, and pay exactly what you have to pay and nothing else. So deep learning exploded, right? But let's look at a concrete application. Every year, there's a competition called ILS VRC among research teams across the world. And what they do is they take that ImageNet data set, which is a very large data set, which is composed of images with a single thing in them. So it's either animals or objects or plants, no humans. And they have thousands of categories, and they have to predict the right category for each image, right? That's the game. So actually, they can predict 5 categories for each image, and if the correct category is in the top 5, then it's considered a win, okay? And so they've done this for years and years and years. Here's an example. These are real images from the data set. So who thinks these dogs are, so it's not the same dog, but are they from the same breed? All right. Who thinks they're not the same breed? Do we have any Eskimos or Norwegians in the room? All right. Norwegians are usually pretty good at this. Yeah. And who has no ID? All right. Okay. Well, personally, I have no ID, and I think if you gave me 15 minutes, I would still have no ID. Right. Some things tell me it's the same. Some things tell me it's not the same. Right. So for the record, it's not the same breed. Okay, but how would you know, right? How would you know? Unless you're a real dog expert and you could actually explain to me that, oh, see the difference here and here and here, okay. And then I show you a different breed and you're not an expert of those dogs and you don't know, right? So that's that informal knowledge we need to fit into the computers. So they've been playing this game with dogs and plenty of other categories for years, and these are the results. So they started in 2010, and the blue line is the error rate. Okay, so it goes from 28 to 25 to 16 to 11, down to 3% last year. Okay, only 3% error. And the red bar is how deep, how many layers the neural network that won was. Okay, so in the first couple of years, it was just 1 layer, and then it went up, as you can see, 8, and 19, and 22, up to that crazy number of 269 layers. Okay? So now the question is, what do you think the score would be for humans, right? Normal humans. If I gave you the ImageNet data set, all right, and lots of coffee, and I asked you to score, well, it's millions of images, so it would take a while, but okay, theoretically, you could do it with lots of coffee. What would be your average error? I have no idea. Well, I guess our brains have much more than 269 layers. Okay? So, but still, our brain is different. So what would be the score? Who says less than 5 or less than 3? Who thinks humans would actually beat the machine? No one. Okay. Who says more than 10%? Okay. And between 5 and 10? All right. Okay. So the answer is actually 5. 5.1, if you want to be exact. Okay? But again, it's theoretical, because if I give you maybe 50 images, you would do this. If I gave you 1,000 images, maybe not so much. If I gave you 1,000,000 images, you would never get to the end, right? So the computer can do it faster, longer, is never tired, and it will give the same answer all the time. So what this means is actually deep learning models and computers are now better at recognizing stuff than us, right? I would say, given the condition that they actually have been trained on it, of course. If you show them something they've never seen, right, they won't know. And maybe we will, because we're smarter, right? But still, it's an impressive number, and I'm sure it will keep going down. So this is just one example. There are many more applications of deep learning, and we'll see a few more as we go. But now let's try to talk about how you can actually, oh yeah, please, you have a question. What does it mean, a layer? Means this, in the top right corner. So a layer is a set of neurons that are connected to the previous layer and to the next layer, and they all work in parallel to do some computation, right? So at the minimum, you will have an input layer, okay, which will be your input data. So let's say my pixels, right? So let's go back to my 1,000,000 pixel example. So I would have 1,000,000 input neurons, okay, each of them with the input with 1 pixel value, and the output layer would be probably the number of categories I have. So let's say I have 1,000 different categories, okay? So I would have 1,000 neurons in the output layer, and I would just want one to be activated for a given image, right? And in the middle, I've got what we call hidden layers, which are just additional layer of neurons that do their magic, right? That just extract features, we'll see some examples, extract features from the input layer and gradually learn how to activate the correct output neuron for a given input, right?
Does it mean when you add one layer, you get exponentially increasing connectivity?
So there are different structures. In this example here is what we call a fully connected network. So each neuron is connected to all the inputs and all the outputs of the previous and next layer, okay? But there are different architectures, right? And now you start to understand why it's so heavy from a computation point of view, right? Because it's N1 times N2 times N3 times, so it's a lot of connections, and each of them has to be optimized and computed. Yeah. Training is, we'll do some live training on a smaller data set, right? You'll see that. Okay, so now let's talk about what we do at Amazon. So actually, Amazon has been doing lots of AI for, I want to say forever. It's probably not quite true, but feels right. Amazon was started in '95 and as a bookshop, as you know. And if you go to the internet and look for screenshots of the early website, very early on you had recommendation, right? And then you had content personalization, etc. So very early on, they felt they had to have that smart feeling to the website, right? That custom experience to the website. And then as time went by, Amazon started to use AI for their what we call the fulfillment centers, so where the goods are actually stored and where they're shipped from. You may have seen those videos on YouTube of the Amazon robots that pick up the shelves and move the shelves to the humans so that they can pick the objects and prepare your order, right? If you haven't seen this, you should take a look. Just look for Amazon Robotics on YouTube. And today we have more than 40,000 robots live every single minute in all of our fulfillment centers, just moving around and autonomously and moving stuff so that we can all get our orders in time. Of course, there's tons of AI and machine learning on the website. If all of us went to the same web page on Amazon, we would not see the same thing, for sure, right? We would see different products, different layouts, different everything, actually. And I'm sure you've seen this, although I don't think it's available in Italy, but it's available in the UK and in Germany and in the US, so hopefully, and not in France, hopefully soon. So the Amazon Echo family of devices, the personal assistants, and you can just talk to them and order a taxi, order a pizza, ask for the news, ask for weather information. Every single day we have new skills, as we call them, that come out for the Echo devices. And it's evidently all based on deep learning technology, natural language processing, text-to-speech, etc. Right? So that's a consumer product. That's, I would say, the visible side of all the work that Amazon is doing on AI, right? But there's, of course, we're developers, so we want to build stuff. And there's a full stack of AI and machine learning solutions and services that are available in AWS, right? Starting from, of course, the infrastructure, the instances. So obviously we have CPU instances, we have also GPU instances. I'll show you one in a minute. We'll do some training. On top of this, we could run your favorite deep learning libraries. So today I'm going to use MXNet, but you could use TensorFlow or Keras or something else. Then if you want to actually go deeper and really do, build your custom algorithms and your custom applications, you could use our EMR service, which is basically a managed service for the Hadoop ecosystem, to do Spark and all the other Hadoop friends. You could do Amazon machine learning, etc., etc. So we have a full set of services that allow you to build smarter applications. But you need to be an expert, right? And although we all have machine learning and soon deep learning on our resumes, right? Not everyone is an expert, okay? So we thought, and our customers asked us to do that it might be interesting to build some higher level services, right? Which are just an API call away and very simple to use, and yet able to do very complex things. And these are the three services that you see on top, Lex, Poly, and Recognition. And I'm going to talk about those for a minute and then show them to you. Okay. So the first one is Poly. Well, it's easiest to explain. Poly is text-to-speech, right? So it's just one API call, select a language, select a voice, and you get the sound file in real time with a human-sounding voice. So today we have 24 languages, including Italian, so we can try that, and 48 different voices, okay? And we'll keep adding more. The next service is Lex. So Lex is a chatbot service, so you can design a conversational interface using text or using, again, voice, and integrate that in the AWS platform with your web app or your mobile app or on Facebook or on external channels. So pretty cool service if you're into chatbots. And the last one is Recognition. So Recognition is image recognition. So it can do object detection and face detection, face comparison, etc., etc. And as you can imagine, all these are obviously based on deep learning. But all you have to do here is just call an API, right? So let's give it a try. Okay. So of course we could play in the console here and Recognition and Poly. Oh yeah, we want to try the Italian, all right. Could I have the mic for a second? Thanks. All right. Okay, so that might be a little small. Okay, so here are all the voices that we support, right? And so for Italian, we have two voices. We have Carlo and Giorgio. Very Italian names, so let's try this. Hopefully I have sound, yeah. Oh no, I don't. It's coming, oh, it's on the HDMI. All right, that's okay, we can do this.
Che digiterai qui.
Okay, let's try that again.
Ciao, mi chiamo Carla. Leggerò qualsiasi testo che digiterai qui.
Okay, so that's Carlo, and let's have Giorgio.
Ciao, mi chiamo Giorgio. Leggerò qualsiasi testo che digiterai qui.
Okay, and you can go totally stupid, and if you want to do you have anyone from Iceland in the room? No. Too bad. Okay. All right, let's do Icelandic.
Ég heiti Dóra. Ég les upphátt allan texta sem þú skrifar hér.
Okay, all right. Well, we could do this all day, but that's not the point. Thank you. Okay, so as you can see, this is really just an API call. So I could do this. I could do this on my laptop too. We'll do it on the robot afterwards. Okay, I can just show you. Yeah, who gives it? Okay, so this is local here. And okay, so that's Poly basically. I want to show you recognition now. So that's Poly, right? 24 voices, 24 languages, 48 voices, and it's extremely fast. So you can either play the sound file and have an interactive thing going, or you can save it and use it in your applications. So very, very easy to use. If you want to see what the API looks like, after all, let's do this. Well, this is it, really, right? That's all there is to it. You select a voice, and the format, which is MP3 here by default, and the text that you want to generate, and that's it. So one API call away, and you get, in real time, a human-sounding voice, okay? And then either you play it or you save it for further use. So that's all you need to do, one API call. You don't have to be a deep learning expert to do this. Okay, let's take a look at the recognition now. So let's take my favorite image. Should I show it to you? Yeah, of course. Okay. Okay, so it's Oktoberfest, but I'm sure we have a Rimini Fest and Bologna Fest, and we have the same thing all over the world, right? Okay, so that's my picture. It's a fairly complex picture. So now let's call recognition on that picture and see what happens. Oh, and oh, sorry. I need to copy that image to S3 so that's my bucket name. Or could we have the sound on the HDMI? No, maybe not. We don't have a tape. Yeah?
You can option click the sound or open.
Oh, wow. So I need to go in my Mac settings? All right.
System preferences.
Okay. I'm going to learn something now.
You can select sound, select the output to the...
Yeah, it says HDMI, so...
just the speakers, so can you just select the speakers? Try.
Let's try this again.
Now you have to put it out, to pipe it to the speakers, not the HDMI.
Oh, okay. See what you mean.
Interface.
Do it the other way.
Yeah.
Okay.
Try again.
Ég heiti
Perfect.
Dóra. Ég les upphátt allan texta sem þú
Okay,
skrifar
thanks.
hér.
I'll be fine, actually. You can hear it, right? Or not? Do you want the mic? Yeah, let's have the mic. Okay, thanks. Okay, so let's send that image to recognition and see what happens. Okay, so pretty immediately I see some labels and confidence.
15 faces have been detected. Here are some keywords about this picture: people, person, human, alcohol, beverage, drink, crowd, female, girl.
Okay, so I would say that's a fairly accurate description of that picture, right? And so, like I said, we've got labels, we've got confidence scores, and then we find 15 faces, which is the maximum number we can find. It's a predetermined limit, right? We stopped it at 15. And for each of them, we get some information like gender, age range, emotion detection, and there's additional information on where the nose is and where the eyes are, etc. But I didn't print it out. So if I show you my script, then highlights the faces that have been found, and as you can see, we see 15 faces, right? And we could check that, okay, face 2 here, that lady here is, where is she? Okay, here she is. Okay, she's female, she looks pretty happy. Well, she looks to be closer to 23 than 14, but okay. Pretty safe. Oh, by the way, never do this with your girlfriend, okay? Never take a picture of your girlfriend and use this, never, right? Or your wife, never, right? Or your mother might forgive you, but your girlfriend will not. Okay, trust me. All right. Okay, let's try a different one, just for a second. Okay, so I'm not showing you this picture for now.
A single face has been detected. Here are some keywords about this picture: city, downtown, metropolis, urban.
Okay, and obviously that's Poly that you hear here. I'm extracting some outputs and sending them to Poly. Okay, so let's see how fast you can find the face, because there is a face in here. Ready? All right. So it's a larger crowd, but we usually with smaller groups, I have like I ask people to raise their hand when they see the face, and yeah, thanks. But for some people it takes a few seconds, right? So because it's way over there, and it's hidden in this very complex picture. And it's interesting to see that the cartoon face is not picked up, because it's not a face, because no one has eyes half the size of their face, at least not where I come from. Or maybe after a very, very long evening abusing substances, but in general case, that's not a human face, right? Okay, so this is recognition, okay? Pretty cool. But and you will find all the code and everything. Again, it's on GitHub. I can just show you the Rico API. It's super easy as well. Okay, so this is the one to detect faces, right? Again, single API. You literally copy the image to S3 and point recognition to it. Comparing faces needs a source image and a destination image. But as you can see, and detecting an image, again, is as easy as this, right? Where the image is, how many labels you want, and what's the minimum confidence score that you want to report, okay? So, pretty smart services, but if you're a very bad Python developer like me, you can use them in minutes, right? You don't have to be an expert. Okay, but there's a problem with this. Okay, and yeah, we have tons of customers. Let me mention a few. The Washington Post is using Poly in their mobile app to read articles, right? So you don't have to look at your phone like this. You can just click play and let let the Washington app read the article to you, right? And you can actually focus on what's outside, which is nice. And you know, Capital One is one of the top 10 banks in the US, a very large bank. And they have a Lex application for people to use to have information on their banking details, right? So you can just, instead of going to the bank website and looking at the detailed report that we never quite understand, you can just use a chatbot and say, okay, how much did I spend on restaurants last month, right? That kind of thing. So that's very, very cool. So again, like I said, there is a problem with what I showed you, right? I would say in the context of you know, devices and robots, etc. The problem is we need the cloud, right? We need the cloud connection. We need network connectivity. And sure, I could use recognition and everything on my robot over there. So maybe it's time to bring the robot now. So, okay, here's my friend. So it's a Raspberry Pi robot. So sure, I can connect to that little guy. And I could use Poly to do tons of silly things, like this.
Hello, friends. Thank you for visiting us today. I hope you'll have a great time. Now, Julian, could you please stop clowning around and get on with the talk?
Right. Thank you. And thank you to Air France for not crushing the robot this time. Yeah, it's a pretty regular event. I keep fixing it, but now it's okay. So yeah, you know, it's a Raspberry Pi. It has a Wi-Fi key. It can connect to the internet. I can use anything I want with this. Okay, it's a Linux system. But can we expect all the robots of the world and all the devices of the world to be always on, always connected to the cloud? Probably not, right? It's an unsafe assumption. Autonomous cars and stuff, right? You go in a tunnel and then what happens? So we need something different, right? Something that could work and not be cloud-based. And this is what I'm going to talk about for the rest of the presentation. We can build deep learning applications using MXNet and embed them on devices like this, which are not powerful at all, right? This has a 1 gigahertz clock speed and 1 gig of memory. So it's a very, very small device if you compare it to a typical computer or server, right? And we're going to do local AI on this little fellow here without any cloud connection. So a few words about MXNet first. So MXNet is for programmers, right? It's really, like I said, it's developer friendly. It supports multiple languages, like of course Python, C++, JavaScript, MATLAB, and Julia, and I'm sure I'm forgetting something here. It's an Apache project, so it's open. It's not controlled by any company. AWS has committed to supporting this project because we think it's the most appropriate, and I will explain why in a minute. Both for cloud-based application and for smaller devices. And I think in the top 10 MXNet committers, we have 4 or 5 people working for AWS right now. It's high performance. You know, as you will see, even on a small device like this, it runs fairly fast, and it doesn't require gigabytes and gigabytes of memory, right? And like I said, we endorsed it because for all those reasons, and also because in a wider context, it scales very well, right? So why is scaling important? Scaling is not really important at this stage. Scaling is important when you train the model, right? So when you actually take those million of images or those terabytes of sound bytes, etc., and you train the model, okay? This is where the operations are the heaviest. And so you want to be able to use as many GPUs as you can to speed up training, okay? And MXNet can do this very easily in the code, and it can do it very efficiently when it's running on, as you can see here, up to 16 GPUs with almost linear scaling, which means if you train on 16 GPUs, it's pretty much 16 times faster than when you train on one GPU, right? Almost perfect linearity. And it goes beyond this. Why 16? Because 16 is the largest GPU instance that we have, right? The largest instance that we have has 16 GPUs. So in one server, that's the limit. But we can have multiple instances, and we could go up to 256 GPUs, so 16 instances with 16 GPUs in them. And again, as we scale on training on multiple servers, we see almost linear scalability again. And that's something you will not see in other frameworks, right? Most other frameworks can either not do GPU at all, or they can do maybe one GPU, or maybe if you tweak your code like a maniac, you can get it to run on multiple GPUs in the same machine. And that's just one line of code when you do that in MXNet. And then training on multiple hosts, then this becomes a real project if you want to do this with other libraries. For MXNet, it's almost as simple as sharing SSH keys across the nodes so that they can connect to one another, and that's about it, right? The data set will be split automatically and so on. It's really nice. So that's one of the reasons also why we like MXNet. It's because scalability is very important for our customers, and thus it's very important for us. And we want to make sure we build services that scale to the max, right? So let's do some demos. So let's start with something simple. Let's do some training for a second. So here I'm going to use a GPU instance to train an image recognition model on a data set, which is called MNIST. And I guess most of you or some of you have seen this before. MNIST, yeah, it's very popular. It's 70,000 handwritten digits from 0 to 9. And of course, the goal is to show an image and get the proper result at the end, okay? So let's do this. And you can see, where is my instance? Here it is, okay. So here I'm running on a smaller GPU instance. It has only one GPU, but that's more than enough for what I need. And I'm running an Amazon machine image, which is called the Deep Learning AMI, which is built by us, and you can use it at no cost. And the cool thing with this is that it comes pre-installed with everything. So whatever framework you use, Caffe, MXNet, TensorFlow, blah, 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 anything else, it's already in there. So you can just boot up your GPU instance with this image, and everything is ready for you to work. You don't need to go and install the CUDA drivers and the NVIDIA stuff, which is a little tricky to do, okay? And so here, whoops. Okay, I wrote, MXNet, yeah, MNIST, all right. So I designed a very simple model, right? So it's 30 lines of code, right? To do everything. So it's like, when I say it's developer friendly, it really is. It's very high level, right? So you don't have to go and coming back to your questions earlier, you don't have to go into the details of every single neuron and just define layers, connect them, and that's it. Okay, and that's what I'm doing here. So I've got a series of blog articles on this with every single detail explained, so I'm going to go a little faster here because I want to get to the point. Basically here, you just load the data set, right? So you load those images. There's a training set that we'll use for training, and there's a validation set that we use to evaluate the quality of the model, just like we do in machine learning. Okay? This is the network definition. Okay, so an input layer. Then a first hidden layer, fully connected. A second hidden with 128 neurons. A second fully connected layer with 64 neurons. And then the output layer with 10 neurons. And 10 is not a surprise, it's because we have 10 categories, right? From 0 to 9. Okay, so we need to figure out what digit this is. And that's all it takes, right? That's all it takes to define my network. Okay, define the layers, define how they're connected, define how many networks, how many neurons are in each layer, and that's it. So we have multiple types of networks, but this is the simplest one. And as you can see, it's only 6 or 7 lines of code. Okay. Then I bind my data to that model. Okay, the data I loaded. I just say, okay, this is what you're going to train on, and now you train. Okay. Then I'm saving the results, so I'm saving all the weights for all the layers, right, because I want to reuse it afterwards. And then I use my validation set to measure the accuracy of the model, okay? So, not a lot of code, right? So let's do this. How do I train it? Just like this. So it's gonna load the data, and then it's going to run for, I think it's 10 epochs. So an epoch is learning the full data set once. Okay, so here I'm taking that data set and I'm sending it 10 times into my model, okay? Batch by batch, but the full set goes 10 times in a row into the network. And I can see my training accuracy going up, right? And actually, if I let it run for a little more, let's give it maybe 30 epochs, you will see it gets to 1, okay? That's that universal approximation theorem I mentioned, okay? So it's gonna learn that data set perfectly. It's gonna learn the training set perfectly. But then, when I take the validation set and I run it, of course I get a lower score, because these are images that the network has never seen before, okay? So again, yeah, we'll get to 1. Okay, so maybe I need 32 or 35 epochs, right? Okay, so training accuracy almost gets to 1, and then validation accuracy is 97%, okay? And then I could use some handmade digits that you can see here. So I did them myself, and I could try and run them through the network, right? So I'm going to load each image and load the model that I trained and just run it through there, okay? And do this and see what the scores are. Okay, so, so you can see 10 probabilities, right? Because obviously we have 10 categories. So they're pretty close to 1. They're not perfect, but they're pretty close to 1. So the first image is a 0, and the second, and all these are pretty good. And well, the 9 is not so great. The probability is lower, but we're still okay with the fact that it's a 9. Okay, so I could have a better network, I could train for longer, I could improve everything, etc., etc. Okay? But okay, that's just a very simple model here. Now I want to do something more complex, right? I want to be able to do that ImageNet thing I mentioned earlier. I want to do it here. I want to use a pre-trained network, right? Training on ImageNet takes a while. I cannot do it here. And I want to take that model, train it in the cloud, using the cloud scalability, save it, and then copy it in there and use it locally, okay? And that's what I'm doing here. So let's go back to my robot here. So here's the model I'm talking about. It's the Inception model. It's 44 megabytes, so it's not huge, but it's a fairly advanced model. Okay, it's been trained on ImageNet, and I'm going to do pretty much the same thing that like you saw here. I'm going to load the model, and I'm going to ask the robot to recognize images, right? But to make it a little more fun, actually, I'm going to have the robot take a picture of objects, right, using the camera down there, and recognizing that, okay? So it's all in Python. It's fairly easy to do, and we just have to start that server. And hopefully it still works. Okay, yeah. Yeah, the loudspeaker is on. So can the thing move or not? All right, okay. Okay, so just to make it a little more even difficult to set up, okay, I've got this thing here. So it's an Arduino, which is Italian, right? Or something. So it's an Arduino with a, well, I guess it's a PlayStation joystick connected to it. And here, this has nothing to do with deep learning, but it's pretty funny, so why not? Oops. And it's an IoT thing, okay? So I'm using the IoT service of AWS to, through Wi-Fi here, to send messages back and forth to the cloud. So from here to the cloud, to the robot, etc., okay? So I can drive that thing. Can you see it? Yeah. So I'm making sure it's not falling off. That's why it's stopping. Okay, so let's have an object somewhere. Okay, I'll take my lucky object, the one that should work. And then if you want, we can try something else. Okay, I need to cheat. It's not, yeah, okay. Yeah, you know, I keep saying it's a running, I mean, it's an old joke now, but sorry, I have to do it again. But some people think robots are going to kill us all, but we're quite safe. This one is very friendly. He's got a Twitter page. You can follow him on Twitter. Okay, so I'm going to try something else that's probably not going to work either, but okay, fine. So have you seen this before? It's the IoT button. You just click it, and it sends an IoT message to AWS IoT. And so this one, if it gets through, if not, I will fake it. That's right. We'll send a message to the robot asking it to take a picture. Oh, yes, it is working. And telling it what it sees.
I'm 98% sure that this is a baseball.
All right.
It's 31 centimeters away.
Okay, thanks. All right, bring me your objects now. Okay. All right. Yeah, I'm up for that. Okay. So I click here, sends an IoT message to AWS IoT in Dublin. The robot gets it, so it's back and forth to Ireland. As you can see, it's pretty fast. The robot takes a picture. Come on. The robot takes a picture with the camera and uses the local MXNet model to detect it. This button has been giving me trouble, so I should try something else. Oh, come on. Okay, I can fake it. That's okay, no worries. Works only once. Come on. Just use violence. Yeah, see? That works.
I'm 69% sure that this is a water bottle. The
right.
object is 51 centimeters away.
Okay, pretty good, right? So, you know, it's all fun and everything, and of course we're going to try those and it's going to fail. Because this is a really small object, I don't I don't know what the distance should be, maybe here. So once again, what happens is, okay, there's the IoT thing going on. And there's Polly, right? The voice comes from Polly, as you can understand, as you can imagine. So I really need to hit it, right? Come on, work. Okay, I'll fake it. I can send the message from here as well. And so it takes a picture. All right, that's my complex protocol. No, it's quite dead, is it? Come on. Oh yeah, here it goes.
I'm 13% sure that this is a pole. The object is 22 centimeters away.
What did he see? Oh yeah. Oh, lighter is in there. Hey, I get 5. Remember, I get 5 categories, so I won. So now this is not going to work at all. I'm quite sure because it has a picture, and if you show it a picture of something, it gets it wrong. So if you have some other objects, do you have a laptop or something? Laptops usually work. We can try that and then conclude before they kick me off the stage. You want to try? Yeah, I don't have much in here. Oh. Okay, we can try this. All right, last one, right?
This is giving you a headache? So
Oh man. Yeah, okay, fine. That's a tough one. No, that's never gonna work. Come on. Yeah, I'm very dependent on my phone here, and it's not working great. Yeah, here we go.
I'm 67% sure that this is a thimble. The object is 20.
What? Okay, pill bottle, man, it's in there. Come on. Hey, I still win. All right, they're going to kick me off the stage. All right. So, Julian 1, Rimini 0. Okay. All right, so, oh no, I don't need this. Thanks. So, I'm getting to the end. I mentioned the deep learning AMI already. Again, I went very fast because there's so much stuff I wanted to show you today. Keep you hopefully interested. You will find all this stuff in detail on my Medium blog. So just go to medium.com, Jules Simon. Well, it's easy to find. And you will find all the tutorials to get started with MXNet, to do training, etc., how to do the Raspberry Pi thing, etc., etc. Okay, so it's all out there. All right, there are plenty more resources. There's one I want to mention. I recorded an AWS podcast a couple of weeks ago with an introduction to MXNet. So just look for AWS podcasts, MXNet. There's only one, and it's mine. So you can listen to that and get some additional information. Okay? So I want to say grazie mille, thank you, danke schön, merci, gracias, and I'll stop there. I cannot do the 24 voices. Thank you very much, EuroPython, for having me. Thanks for listening, and if you have questions, I'm here.
Well, thank you very much, Julien. It was an amazing talk. Thank you, the little robot. I don't know, does he have a name or something? So this is the end of the afternoon session. There is a sprint orientation going somewhere. I don't know where exactly. All right, yep. Yeah, so thank you very much. Let's give Julien another round of applause, and then we can break for the...